Hello there and welcome to Life Beyond Scene, where the quietest places on Earth sometimes turn out to be the ones with the most to say. Imagine standing at the edge of a small lake in the Czech Republic. The water is green, almost turquoise in the right light. Limestone cliffs rise around it, pale and weathered. The valley is calm, there are trees, there is bird song somewhere behind you. If you did not know what you were looking at, you might think this was just a pretty spot for a walk on a Sunday afternoon, the kind of place where people bring sandwiches and sit on the rocks and let the afternoon go by slowly. But the water is warm, slightly warmer than it should be, given the air temperature, given the season, given everything you would expect from a small lake in the middle of Moravia. And if you lean close enough, there is a faint smell, something mineral, something slightly chemical, like the air near a hot spring or an old bathhouse. And if you were to drop a line into that green water and just keep dropping it, you would find that it does not stop where you expect it to. It keeps going and going and going, past the point where light exists, past the point where most diving equipment can function, past the point where any human being has ever been, and then even past that into a depth that no instrument we have sent down there has yet managed to reach the end of. This is the Hranice Abyss. In Czech, it is called Hranice Propast. It sits near the town of Hranice, in the Olomouc region of the Czech Republic, tucked into a quiet corner of Central Europe that most people outside the region have probably never thought much about. And it is, as far as we currently know, the deepest flooded cave on Earth. Not the deepest ocean trench, not the deepest mine shaft, not the deepest anything carved by human hands, the deepest flooded cave, a natural passage in the rock filled with water that descends to a depth of at least 473.5 meters below the water surface. That measurement was verified in 2016, and the reason the word "at least" is doing a lot of work in that sentence is something we will come back to. Because that number, as large as it is not the full depth of the cave. It is simply the deepest point that any instrument has managed to reach before running out of cable. The bottom has not been found. We do not know how much further it goes. There is something quietly remarkable about that. We live in an era when satellites map the surface of Mars in extraordinary detail, when deep-sea submersibles have visited the Mariana Trench multiple times, when it feels like the age of genuine geographic mystery should be mostly behind us. And yet here is a flooded cave in the Czech Republic, a country in the heart of Europe surrounded by roads and towns and centuries of human settlement, and we cannot tell you how deep it is. We have tried. We have sent divers and robots and instruments, and the cave has simply continued downward past all of them. Before we go any further down, I want to pause for a moment and ask you something simple. Where are you right now as you listen to this? What time is it where you are? Is there water nearby tonight? A river, a lake, rain on the window, maybe just a glass on the table beside you? I ask, because this is a story about water, and about depth, and about what lies beneath surfaces that look perfectly ordinary. And sometimes it is nice to know where people are when they encounter a story like this one. If this is the kind of thing you enjoy, the slow, careful exploration of places and ideas that do not get enough attention, I would really appreciate it if you like this video and subscribe to the channel. It helps more than you might think, and it means these stories can keep being made. There is no pressure, of course. But if you are still here and you're finding this interesting, that little gesture genuinely matters. Thank you. Now, the Hranice Abyss. The name itself is simple enough. Hranice is the name of the nearby town, a modest Czech municipality of around 20,000 people, the kind of place with a main square, a local church, a train station. Propast means abyss or chasm. So the name is just, more or less, the Hranice Chasm. Straightforward, local, completely unassuming for something that holds a world record. The cave sits within a landscape known for its limestone geology. The Olomouc region, and the broader Moravian area of the Czech Republic has karst terrain, meaning the bedrock is largely made of soluble rock that groundwater has been carving and dissolving for millions of years. Caves are not unusual in this part of the world. The Moravian Karst region to the south is famous for its cave systems, visited by tourists every year, lit up with electric lights, fitted with wooden walkways. Caves are a known feature of this landscape, but Hranice is different from those caves. Different in its origin, different in its chemistry, and very different in its depth. Where most caves in the region were formed by rainwater, trickling down through the rock over thousands of years, the Hranice Abyss was formed by something coming from the other direction entirely, something rising from below, something that has been working at the rock for far longer than most caves have existed. And the result is a void in the earth that drops nearly half a kilometre below the surface of the water, with no confirmed end. 473.5 metres. It helps to put that in terms of something more familiar. The Eiffel Tower in Paris is about 300 metres tall from base to tip, so the confirmed depth of the Hranice Abyss is more than 1.5 Eiffel Towers stacked on top of each other, measured straight down from the waterline. The Empire State Building, including its antenna, reaches about 443 metres. The confirmed depth of this cave is deeper than that. And again, that is just the confirmed depth. The actual bottom, if there is one within any range we can currently imagine, could be considerably further down. What makes this particularly striking is not just the number, it is the location. This is not a remote cave in an unexplored jungle. It is not buried under an Arctic ice sheet or hidden in some barely charted mountain range. It is in the Czech Republic, in Moravia, near a town with a train station. People have been aware of this place for centuries. There was a spa resort built nearby in the 19th century, because the warm mineral water was thought to be good for your health. People soaked in it, they bottled it, they recommended it to friends, and the whole time beneath the gentle, warm, slightly fizzy surface of that little lake, the cave was there, going down and down and down into the dark. The central tension of the Hranice Abyss is exactly that gap between appearance and reality. From above it looks like a flooded quarry, a scenic one maybe. The kind of place that gets photographed for regional tourism brochures. The water has that blue-green colour that limestone water often has, clear near the edges, darkening toward the centre where the depth begins. The limestone walls around it are pale and textured, carved smooth in places by water and time. It is genuinely pretty. But that surface is a kind of lid, and what is underneath it has resisted every serious attempt to fully understand it. Divers have gone in and come back changed by the experience of floating in passages that go on beyond the reach of any light they carried. Robots have been lowered on cables until the cables ran out and the passage was still continuing. Scientists have studied the water chemistry and the rock structure and the geophysical signals from the surface, and all of it points to the same conclusion. This cave is deeper than anything we have been able to measure, and the processes that formed it are still in some sense ongoing. That last part, that the cave is still actively being shaped by geological forces happening right now, is something worth holding on to as we go through this story. Because Hranice is not a relic. It is not a finished thing that formed millions of years ago and has been sitting quietly ever since. The warm water rising from below is still carrying dissolved gases, still chemically aggressive, still slowly eating away at the limestone walls. The cave is alive in the geological sense, it is still becoming something, and we do not yet know what. The year 2016 is a significant marker in the story of this place. That was when a team led by Polish cave diver Krzysztof Starnowski, working with support from National Geographic, sent a remotely operated vehicle into the cave and measured a depth of 473.5 metres from the water surface. That number made headlines in the scientific community because it surpassed the previous world record for a flooded cave, which was held by Pozzo del Mero in Italy at 392 metres. Hranice did not just edge past that record. It beat it by more than 80 metres, and the ROV still had not found the bottom when the cable ran out. That is where the official record stands, and that is where the mystery in the most literal sense, begins. Over the course of this story, we're going to go through all of it. The geology that made this cave possible, and why it is so much deeper than almost anything else on Earth. The history of how humans discovered it, and the slow, careful, occasionally dangerous process by which divers pushed further and further into its depths over decades. The specific people who made those dives, what they experienced, and what they found. The science that has been done from the surface, using instruments that do not require anyone to go in at all. The biology of the cave, which turns out to be quietly extraordinary in its own right. The technology question, which is really a question about what it would take to actually reach the bottom. And finally, what all of this says about the nature of unknown things, and how many of them are still out there, hiding in plain sight beneath surfaces that look completely ordinary. But before any of that, we need to understand what kind of place this actually is. Not just the numbers, not just the record, but the physical reality of being there. What you see when you stand at the edge, what the water smells like, what the first divers encountered when they went in, what the cave looks and feels like from the inside, at least in the parts that human beings have actually been able to reach. Because a cave is not just a measurement, it is a place. And this one, despite everything that makes it extraordinary, is also a real, physical, specific location in the world. Limestone walls, warm water, the smell of something old and mineral and deep, and below that, the dark. The town of Hranice sits in the Olomouc region of the Czech Republic, in a part of the country called Moravia. It is a quiet, mid-sized town, the kind of place with a central square, a few churches, some older buildings mixed in with more recent ones, a train station that connects it to the rest of the country. The surrounding landscape is gentle and agricultural for the most part, rolling fields and patches of forest, the kind of Central European countryside that does not announce itself dramatically. The Bechva River runs nearby. There are hills. It is, in the most honest sense, an ordinary-looking part of the world. And then, a short distance from the town centre, there is this. The cave entrance sits within a small nature reserve, surrounded by limestone outcrops and vegetation. When you approach it, what you see first is the lake. It is not large, roughly 50 metres across, roughly oval in shape, sitting in a depression in the rock like a bowl that has been filled with water. The colour of the water is one of the first things people notice. It has that particular blue-green quality that limestone water often has, clear and slightly luminous near the edges where the water is shallow, shifting into deeper turquoise and then into a darker, more opaque blue toward the centre, where the bottom drops away and the light simply stops reaching. On a sunny day, the colour is genuinely striking. It photographs well. It looks like the kind of place that would attract visitors for purely aesthetic reasons. And it does. The limestone cliffs and walls around the lake are pale grey and cream-coloured, weathered and textured, carved over time by water and by the slow mechanical pressure of freeze and thaw. Vegetation clings to the ledges. In places the rock is smooth and rounded. In others it is jagged and fractured. The whole site feels enclosed, a little hidden from the surrounding landscape, which adds to the sense of it being its own particular world. You could stand at the edge of that lake and feel, reasonably, that you are looking at something beautiful and slightly unusual, but not at something that defies comprehension. Not yet. The smell is one of the first hints that something different is happening here. There is a faint but distinct sulphurous quality to the air near the water's surface. Not overwhelming, not unpleasant exactly, but unmistakable once you notice it. The kind of smell you associate with hot springs or geothermal areas, a mineral, slightly organic note that tells you the water is coming from somewhere deep and warm. And it is warm. The surface water at Hranice sits at around 14 degrees Celsius, which is noticeably warmer than you would expect from a lake in this part of Central Europe, where groundwater temperatures tend to be much colder. In winter, the contrast between the warm water and the cold air sometimes produces a light mist over the surface. The lake does not freeze. That warmth is not incidental, it is a clue. It means the water is not primarily coming from rain or from surface drainage. It is being fed from below by geothermal springs rising from depth, carrying heat and dissolved minerals from far underground. The water has a slightly fizzy quality too, caused by dissolved carbon dioxide, which gives it a faint effervescence that you can sometimes see near the edges as tiny bubbles rising to the surface. This is part of why the water was considered medicinal in the 19th century. Mineral-rich, warm, slightly carbonated, it had the character of a natural spa water, and people treated it as such. They were not wrong to find it unusual, they just did not know how unusual the source of it actually was. If you were to enter the water, which requires permission and proper equipment given the protected status of the site, the first thing you would notice is that the visibility is good. The water is clear. Limestone cave water often is, because the filtration through rock removes most of the particulates that cloud other bodies of water. The walls of the cave in the upper section are pale and smooth in places, rough and irregular in others, covered in places with a thin layer of mineral deposits left behind by the constant flow of geothermally influenced water. The passage in the upper section is reasonably wide, not comfortable by any means, but navigable. The light from above filters down for the first several meters, giving the water that luminous quality visible from the surface. Technical divers, meaning those trained and equipped for cave diving beyond recreational limits, can reach the first 40 meters or so of the cave. This upper section is where most of the first-hand human observation of the cave's interior has taken place. The walls are limestone, of course, and in places they show the characteristic pitting and scalloping that you see in caves formed by flowing water, though the formation process here is somewhat different from most caves, as we will get to. There are areas where the passage narrows, requiring divers to move carefully, to be aware of their equipment, to think about their position. And then there are areas where it opens up into larger chambers, where the walls recede and the space around you expands, and you realise you're inside something considerably bigger than the narrow passages suggested. The transition from the lit upper section to the deep dark of the cave below is gradual. The light from the surface fades. The diver's own lights become the only source of illumination. The walls, if you can see them, show the same pale limestone, but the textures become less familiar as you go deeper, less like the cave surfaces you might recognise from photographs of tourist caves, more raw and irregular. The water remains clear. The temperature begins to change. Despite the geothermal warmth that feeds the surface lake, the water cools as you descend into the deeper sections, which is counterintuitive but has to do with the mixing of different water sources within the cave system. It gets colder as you go down, and quieter, in that absolute way that deep underwater spaces are quiet, where the only sounds are your own breathing and the mechanical sounds of your equipment. The smell of sulphur does not follow you down, obviously. Smell does not work underwater. But the chemistry that produces it on the surface is present throughout the water column. The dissolved gases, the mineral content, the slight acidity of the water, all of it is there, invisible, moving through the rock, slowly doing what it has been doing for millions of years. The cave is not just a space, it is a process, and the water moving through it is the agent of that process, patient and relentless in a way that is genuinely difficult to hold in your mind. One thing that is easy to underestimate from descriptions alone is the sheer darkness of a cave at depth. Not dim, not shadowy, not the comfortable darkness of a room with curtains drawn. Complete darkness. The kind where your eyes do not adjust because there is nothing for them to adjust to. No photon reaches the deep sections of Hranice from any natural source. The rock above, the water around it, the passage walls, all of it combines to create a darkness that is as total as any darkness on the surface of the earth. When divers describe floating in the deeper sections of this cave, the darkness is always part of the account. Your lights illuminate what is immediately in front of you. Beyond that, nothing. You're a small bubble of light in an enormous dark space, and you have no reliable way of knowing how large that space actually is. The cave's geometry changes as you go deeper, based on what divers have been able to observe, and what measurements suggest. The upper section is relatively consistent in character, but around and below the diver-accessible zone, the cave appears to open into larger void spaces. Stanowski and others who have pushed into the deeper sections have described the passage narrowing at certain points, requiring careful navigation and then opening again into spaces that feel much larger, where the walls are out of reach of their lights. This alternation between constriction and expansion is typical of hypergenic cave systems, where the dissolving process creates irregular, often bulbous chambers connected by tighter passages. It is not a smooth, uniform shaft going straight down. It is more complicated than that, more organic, shaped by the specific chemistry and pressure of the water that formed it. The water at the surface has been analysed extensively. It is a mixture of two distinct components. One is the geothermal water rising from depth, warm and mineral-rich, carrying the chemical signatures of its long journey through deep rock. The other is cooler, fresher water that has infiltrated from the surface through the surrounding limestone. The two mix in the cave, creating the conditions you find at the surface lake. The ratio of these components and the specific chemistry of each tells scientists quite a bit about where the water is coming from and how the cave system connects to the broader underground geology of the region. The geothermal component is the more interesting one scientifically, because it carries information from depths that no diver or instrument has yet directly reached. There is something quietly strange about standing at the edge of this lake, if you have the opportunity, and knowing all of this. The water is warm under your hand. The colour is beautiful. The limestone walls around you are solid and familiar, and below the surface the cave goes down further than the tallest building in New York City, and then further still into depths that have never been directly observed by anything human-made or human-controlled. The gap between what the surface looks like and what the reality beneath it is turns out to be one of the defining features of this place. It looks like a pretty lake in a limestone valley. It is in fact one of the most extraordinary geological features in the world. The local area has long been associated with this water in one way or another. The town of Hranice, whose name in Czech simply means something like border or boundary, has existed in various forms for centuries. The warm mineral water was recognised as unusual long before anyone had the tools or the inclination to understand why it was unusual. People used it. They bathed in it, drank it, built infrastructure around it. The spa resort that developed in the 19th century drew visitors from the region who came for the supposed therapeutic properties of the water. It was a modest but genuine attraction. The cave itself, the flooded sinkhole that feeds the lake, was known, but its depth was not. The technology to measure it, let alone explore it, did not exist. And so it sat there, warm and slightly fizzy and blue-green, being appreciated for what it appeared to be rather than for what it actually was. In a way, that history is part of the story. The cave was not hidden. It was not in an inaccessible location. It was not waiting to be discovered in the dramatic sense of the word. It was known, visited, used. The mystery was not in its existence, but in its depth, and that depth only became legible once the tools to measure it were developed, and the divers with the skill and nerve to go in were trained and willing. The cave did not change. Our ability to understand it did. This is worth sitting with for a moment. The deepest known flooded cave on Earth spent a very long time being appreciated primarily as a source of pleasant mineral water. The bottom of it, or what we know of the bottom of it, was not confirmed until 2016. And even now, after all the technology and expertise brought to bear on it, we still do not know where it actually ends. The surface lake, warm and pretty and smelling faintly of sulphur, is still there, still the same colour, still roughly 50 metres across, still fed by the same geothermal springs that have been feeding it for longer than human civilization has existed. What lies beneath that surface, the specific geology that made this cave possible, and why it goes so much deeper than almost any other flooded cave on Earth, is a story that begins not in the 20th century, or the 19th, or even in any period of human history at all. It begins in the Devonian period, roughly 380 to 400 million years ago, when the limestone that underlies this part of Moravia was being formed at the bottom of a warm, shallow sea. And the process that turned that ancient seafloor rock into the deepest known flooded cave in the world is not the process most people picture when they think about how caves form. It is something older, stranger, and considerably more powerful. Most caves form from the top down. Rain falls, picks up carbon dioxide from the air and from the soil, becomes mildly acidic, and then slowly works its way down through cracks in the rock. Over thousands and millions of years, it dissolves the limestone from above, carving passages and chambers and eventually the kind of cave systems you might visit on a family trip. The ones with the guided tours and the stalactites lit up in different colours and the gift shop at the end. That is the familiar story. Rainwater, gravity, time. It is a gentle and well understood process, and it has produced some of the most beautiful cave systems on Earth. The Hranice Abyss did not form that way. The limestone it is carved into is Devonian in age, which means it was laid down on the floor of a shallow tropical sea somewhere between 380 and 400 million years ago, long before the first dinosaurs, long before the first trees, in a period of Earth's history when the land that is now Central Europe was sitting much closer to the equator and looked almost nothing like it does today. That limestone accumulated slowly, layer by layer, from the shells and skeletons of marine organisms. It was compressed, cemented, buried, and eventually lifted by tectonic movement into the landscape we now recognise as the Moravian Hills. The rock is old in a way that is genuinely difficult to hold in the mind. 400 million years is not a number that means much to human intuition. But the cave that formed inside it is a direct product of that age, because the processes that created it depend on the specific chemistry and structure of rock that has been under pressure and heat for an enormous span of time. What carved the Hranice Abyss is a process geologists call hypogenic karst. The word hypogenic essentially means formed from below, and that distinction matters enormously. Instead of acidic water descending from the surface and dissolving rock on the way down, hypogenic caves are created by water rising from deep underground. This water is geothermally heated, meaning it has been warmed by the natural heat of the Earth's interior as it travels through rock at significant depth. And as it travels, it picks up things. Carbon dioxide dissolves into it under pressure, forming carbonic acid. Hydrogen sulfide is another common component, and when hydrogen sulfide reaches water, it reacts to form sulfuric acid. By the time this water begins rising toward the surface, it is carrying a chemical payload that is significantly more corrosive than ordinary rainwater, and it rises not in a flood, but in a slow, persistent upwelling, pushing through whatever fractures and weaknesses exist in the rock above it, dissolving as it goes. The result is a cave that is carved from the bottom up, or more accurately from the inside out, by water that arrives already aggressive and keeps working for as long as the geological conditions sustain it. There is no ceiling to this process in the literal sense. Rainwater caves eventually reach base level, the water table, and stop. Hypogenic caves are not bound by the same logic. As long as the pressurized acidic water continues to rise, the dissolution continues. The cave keeps growing. And in the case of Hranice, the geological conditions that drive this process have apparently been in place for a very long time, producing a void space that goes deeper than any other flooded cave we have yet found on Earth. This is not a common type of cave. Hypogenic karst systems exist in various places around the world, but they tend to be less well known than the great rainwater-formed cave systems simply because they are often flooded, which makes them harder to enter and harder to study. One of the better-known examples is Lechuguilla Cave in New Mexico in the United States, which was not fully discovered until 1986, and has since been found to extend to a depth of around 489 metres and a total mapped length of over 240 kilometres. Lechugia is also formed by sulfuric acid dissolution from below, and its passages are characterised by the same kind of irregular bulbous geometry you find at Hranice, along with unusual mineral formations that result from the specific chemistry of the dissolving process. Another example is the cave system beneath Movil Cave in Romania, which we will come back to later in this story for a different reason, and Zacaton in Mexico, a flooded sinkhole reaching around 335 metres, was also formed by geothermal, hypogenic processes. These places share a family resemblance, a common origin story, even though they are spread across different continents and different geological contexts. What they share fundamentally is the upward movement of chemically aggressive water through ancient rock, and what that process produces given enough time is depth, considerable depth. At Hranice, the water that feeds the cave and continues to shape it carries a specific chemical signature that geologists have analysed in some detail. The dissolved carbon dioxide content is high enough to give the water a faint effervescence, which is why early visitors described it as sparkling or fizzy. The hydrogen sulfide content gives it the characteristic sulphur smell, mild but noticeable, like a struck match, or the faint hint of something mineral and old. These are not just curiosities or sensory details. They are direct evidence of the cave's origin and its ongoing geological activity. The water is not simply sitting in the cave. It is still moving, still rising, still carrying its chemical load upward from depths that have not been directly measured. The cave is not a finished thing. It is a process that is still happening, just on a timescale that makes human observation feel like a single frame in a very long film. The specific rate at which hypogenic dissolution occurs is difficult to calculate precisely because it depends on so many variables: the temperature of the water, the concentration of dissolved acids, the composition and structure of the rock, the rate of water flow, and how these factors have changed over geological time. But the general principle is that it is slow by human standards and relentless by geological ones. Centuries and millennia accumulate into the kind of depth that Hranice has achieved. The cave did not form quickly. It formed over a span of time that dwarfs anything in recorded history, driven by a process that does not require dramatic events or catastrophic forces, just water, chemistry, and time. One of the things that makes the hypogenic origin of Hranice particularly interesting is what it implies about the cave's future extent, or at least its potential extent. Because the process is driven by water rising from below, and because the geothermal and geological conditions that produce that water are still active, the cave is theoretically still growing. The dissolution at depth is presumably still occurring. The void is presumably still expanding, though again on a timescale that makes the word expanding feel almost misleading in the context of a human lifetime. What it means practically is that the cave we have is not the final version of the cave. It is a snapshot of a process that has been running for millions of years and has not stopped. The specific age of the Hranice cave system is difficult to pin down with precision. The Devonian limestone it is carved into is around 400 million years old, but the cave itself is much younger than the rock. The dissolution process that created it likely began sometime in the Cenozoic era, the last 66 million years or so, possibly much more recently than that. Dating flooded hypogenic caves is technically challenging because the usual methods for dating cave formations, which rely on mineral deposits like stalagmites and stalactites, are not easily applicable in caves that have been flooded throughout their history. Some estimates suggest the active dissolution at Hranice may have been occurring for millions of years, but the precise timeline remains a subject of ongoing scientific discussion rather than settled fact. What is clearer is the mechanism, and the mechanism explains the depth in a way that feels almost logical once you understand it. If you dissolve a cave from below, starting at a point where pressurized water meets fractured rock, and that process continues upward and outward over an enormous span of time, you will eventually produce a void that extends from wherever the water originates, deep in the Earth's crust, to wherever it finally reaches the surface. The depth of the cave is, in a sense, a measure of how far below the surface the process began, and at Hranice, that distance appears to be extraordinary. The geothermal water rising into the cave carries isotopic signatures, suggesting it has travelled through rock at depths of potentially a kilometre or more below the surface. If that is accurate, and the scientific work on this is ongoing rather than conclusive, then the cave system at Hranice may connect, through passages not yet reached or even detected, to water sources far deeper than the 473.5 metres currently confirmed. This is where the geology and the depth record intersect in a way that is genuinely unsettling in a quiet sort of way. The 473.5 metres is not an estimate of the total depth. It is the depth at which the measuring equipment ran out. The geological evidence suggests the cave continues below that point. How far below, and in what configuration, and whether there are accessible passages or simply dissolved rock filled with pressurized water, are questions that remain open. The geophysical surveys conducted at the surface, using seismic and gravity measurements to detect void spaces underground, have identified anomalies consistent with cave passages extending below the confirmed depth. These are not direct observations, they are inferences from surface measurements, and they carry the uncertainty that any indirect measurement carries. But they are consistent with the geological model, and they suggest that the confirmed depth is likely not the true depth. There is something almost philosophically interesting about a cave that forms from below rather than above. The rainwater cave is intuitive. Water falls, finds its way down, carves a path. Gravity and erosion, the most familiar forces. The hypergenic cave inverts that. The force comes from below, the carving happens upward. The cave is a product of pressure and chemistry working against gravity, and the result is a void that extends downward from the surface into the earth, even though the process that created it was moving in the opposite direction. The cave is, in a sense, the negative space left behind by water that has already moved through and continues to move through. You are not looking at a static geological monument, you are looking at the current cross-section of an ongoing process. The sulphurous water that gives the surface lake its faint smell and its slightly fizzy quality is not a remnant of something that happened long ago. It is the active ingredient in a geological process that is still running. The cave is still being dissolved right now somewhere below the point any instrument has reached. The rock at the bottom of whatever passage continues below 473.5 metres is in contact with water that is still chemically aggressive, still warm, still carrying the dissolved gases that make it so corrosive. In geological terms, Hranice is a young and active system, not a relic. This is part of what makes the site scientifically significant beyond the depth record itself. The depth record is striking, and it gets attention, but the underlying geological story is arguably more interesting. Hranice is a window into a process that operates far below the surface of the Earth, and that connects the deep geothermal systems of the planet's interior to the surface landscape in a direct and measurable way. The water in that lake has been underground for a long time, travelling through rock under pressure and heat, picking up its chemical character from the geology it has passed through, and it arrives at the surface still warm, still slightly fizzy, still carrying the signatures of its long journey. Every litre of water in that lake is, in a sense, a message from somewhere much deeper than the cave itself. The same geological conditions that produce the cave also explain the warmth of the water, the unusual chemistry, and the fact that the cave exists in this particular location in Moravia, rather than somewhere more obviously dramatic. The Devonian limestone of the region sits above geological structures that allow geothermal water to rise. The fractures and weaknesses in the rock that the water exploits are a product of the tectonic history of Central Europe, a history of compression and extension, and faulting that spans hundreds of millions of years. The cave is where it is because the geology put it there. The depth it has reached is a function of how long the process has been running, and how favourable the conditions have been. And those conditions, as far as geologists can determine, have been remarkably favourable. The Hranice Abyss is not an accident. It is the logical, if extreme, result of a specific set of geological circumstances that have persisted over an enormous span of time. It just happens to be located in a quiet valley in the Czech Republic, next to a small town accessible by road, with a spa resort that operated nearby for much of the 19th century. The extraordinariness of it is entirely invisible from the surface. Understanding the geology is not just background information for the depth record. It is the reason the depth record exists, and it is the reason the cave almost certainly continues deeper than the current measurement. The process that formed it has not stopped. The water is still rising. The rock is still dissolving. And the question of how far down the cave actually goes is, in a real sense, a question about the depth and activity of the geothermal system that feeds it. A question that reaches well beyond the cave itself and into the deep interior of the earth beneath Central Europe, which is part of why the exploration of this cave has drawn not just cave divers looking for records, but scientists genuinely interested in what the cave can tell them about geology that cannot be observed any other way. The people who went into the water at Hranice, the divers who pushed past 40 metres, and then 100, and then 200 and beyond, were not just chasing depth. They were accessing a geological system that has no other point of entry, and the story of how they did that, and how far they got, and what they found when they got there, begins much earlier than the famous 2016 expedition that put Hranice on the map for most of the world. The story of how people came to understand Hranice does not begin with cave divers or depth records or remotely operated vehicles. It begins, in a way that feels almost too ordinary, with people taking baths. The warm, slightly mineral water at the surface of the site was noticed long before anyone thought to ask how deep the water went. For local communities in the Moravia region, warm spring water rising from the ground was a practical thing, a useful thing. It was warm in all seasons, which was unusual. It had a faint sulphurous edge to it, and a slight fizz when you disturbed it, and it left a particular feeling on the skin. People recognised these qualities as the qualities of medicinal water, the kind of water that had been valued across Central Europe for centuries in the context of bathing culture and spa treatment. The Austro-Hungarian Empire had a rich tradition of mineral spa resorts, and the warm springs at Hranice fit neatly into that tradition. By the 19th century, a spa resort had been established near the site. The water was promoted as having therapeutic properties, and people travelled to the area to take the waters, as the phrase went. The cave itself, the flooded sinkhole beneath the resort, was simply the geological feature that produced the warm spring water. It was a source, not a subject. The depth of it was not a question anyone was particularly interested in asking. The water came up warm and mineral-rich, and that was the useful part. What was below the water was underground, which is to say, it was beyond reach and therefore not a pressing concern. This is worth sitting with for a moment, because it is a genuinely strange historical footnote. The deepest known flooded cave on Earth was, for a significant portion of modern European history, primarily known as a spa amenity. People were drinking and bathing in the geothermal water from a cave that descends at least 473 metres, and the depth of that cave was simply not part of the conversation. The resort closed at some point in the 20th century, as many such establishments did, but the site remained known locally, and the unusual warm water continued to attract attention, just of a different kind as the century progressed. Systematic scientific interest in the cave as a geological feature, rather than a mineral water source, developed gradually in the 20th century. Czech speleology, the study of caves, has a reasonably long and active history. The country sits on significant karst terrain, particularly in Moravia, and cave exploration has been a recognised scientific and recreational pursuit since at least the early 20th century. The Moravian karst, north of Brno for instance, contains several well-documented cave systems that have been studied and mapped extensively. Hranice was somewhat different from these systems, being flooded rather than air-filled, but it drew attention from speleologists who recognised its unusual characteristics. Cave diving as a distinct discipline began developing seriously in the mid-20th century, roughly in the 1950s and 1960s, as diving equipment became more widely available and more reliable. The combination of caving skills and diving equipment opened up flooded cave systems that had previously been inaccessible. Czech cave divers began exploring Hranice in this period, entering the upper sections of the flooded cave with the equipment and techniques available at the time. The early dives were modest by the standards of what would come later. The first roughly 40 metres of the cave are accessible to technical divers without the most extreme equipment, and these upper sections were explored and mapped with reasonable thoroughness. The cave opens from the surface as a roughly circular flooded shaft. The walls limestone, the water that characteristic warm turquoise green. In the upper sections, the cave is wide enough to navigate comfortably, and the visibility in the water, while not unlimited, is workable. Early divers found limestone walls, the expected features of a karst cave, and a passage that continued downward beyond where they could follow it. The measurements from these early dives established that the cave was deeper than the upper sections, which was obvious, and that it was deeper than most flooded caves in the region, which was notable. Depth estimates from the 1960s and 1970s placed the cave at somewhere in the range of 40 to 60 metres in the sections divers had reached, with the passage continuing beyond. This already made it an interesting sight, but the true scale of the cave, the degree to which it exceeded not just regional comparisons but global ones, was not yet apparent. The equipment of the era set hard limits on how deep divers could go and how long they could stay at depth, and those limits were reached well before the cave's passage gave any indication of ending. Through the 1980s and into the 1990s, Czech cave divers continued to push the exploration of Hranice incrementally. Each expedition that went deeper than the last found more cave. This sounds straightforward, but in practice it represents an enormous amount of careful, methodical, physically demanding work. Cave diving at depth requires detailed planning, substantial equipment, and a willingness to operate in an environment where a significant number of things can go wrong in ways that cannot be corrected. The divers who pushed the depth record at Hranice through these decades were doing so with improving but still limited technology, and the picture they were assembling, passage after passage, depth increment after depth increment, was one of a cave that simply did not behave the way caves were supposed to behave. Most flooded caves have a bottom. They have a floor, a point where the passage ends or where it becomes too narrow to follow, or where the water table meets solid rock. The expectation when entering a flooded cave is that you will eventually find a limit. At Hranice, each time divers pushed deeper, the limit was not there. The passage kept going. The cave kept opening into more space below. This is a disorienting thing to encounter repeatedly, and it gradually shifted the perception of the site from an unusually deep local cave to something potentially much more significant. By the late 1990s and into the early 2000s, the cave diving community in Central Europe was well aware that Hranice was a remarkable site. Depth records at the cave had been pushed significantly beyond the early measurements, and the cave had attracted attention from beyond the immediate Czech and Slovak diving communities. The numbers were becoming genuinely difficult to explain within the framework of what was known about flooded cave formation in the region. The cave was deeper than the geology of the surface suggested it should be, which was itself an interesting problem, and one that the geological research would eventually address. But the exploration continued in parallel with the science, each informing the other. It is around this point in the story that a particular name becomes central. Krzysztof Stanowski is a Polish cave diver who had been living and working in the Czech Republic, and who encountered Hranice in the early 2000s. He was already an experienced cave diver with a record of significant exploration in other cave systems, and when he began diving at Hranice, he brought both technical skill and a particular kind of focused attention to the site. He came back repeatedly. He studied the cave's layout, its passages, its behaviour at different depths. He was not the only diver working at Hranice during this period, but he became increasingly identified with the site's exploration, and his contributions through the 2000s pushed the known depth of the cave further than it had been before. The cave diving community outside Central Europe began paying closer attention. Depth records in flooded caves are a specific and somewhat specialised category of achievement, but the numbers at Hranice were becoming hard to ignore. The previous world record for the deepest flooded cave was held by Pozzo del Mero in Italy, a flooded sinkhole in the Lazio region near Rome, which had been measured at 392 metres. Hranice was clearly approaching that figure, and the passage at Hranice showed no sign of ending at that depth or near it. The progression of depth records at Hranice through this period is not always precisely documented in publicly available sources, and the exact figures from individual expeditions in the 2000s vary somewhat depending on the source. What is clear is that by the early 2010s, the cave had been established as one of the deepest flooded caves on Earth, and that it was still being actively explored, and that the bottom had still not been found. Each expedition that pushed deeper found more passage. The cave was consistent in this way, almost stubbornly so. What changed the global profile of Hranice was a specific series of events in 2015 and 2016. In 2015, Stanowski conducted a solo dive that pushed significantly deeper than previous attempts. At roughly 200 metres depth, he encountered a narrow restriction in the cave's passage, a constriction in the rock that required careful manoeuvring to pass through. He pushed through it, and on the other side he found something unexpected. A large void, a space he could not see the edges of. The cave opened up below and around him into darkness that his lights could not fully illuminate. He was alone, at 200 metres, in a flooded cave in Moravia, looking into a space that had no visible boundary. He turned back, as a responsible cave diver must, and began the long decompression ascent. But the implications of what he had found were significant. If the cave opened into a large chamber or continuation of passage at 200 metres, the depth below that point could be substantially greater than the measurements already on record. The cave was not narrowing to a close. It was opening up. The 2016 expedition that followed was a different scale of undertaking. Stanowski partnered with National Geographic, which brought resources and visibility that independent cave diving expeditions rarely have. The plan was to deploy a remotely operated vehicle, an ROV, into the cave to measure the depth below the point where divers could safely go. ROVs are used extensively in ocean research and industrial applications, but using one in a flooded cave presents specific challenges. The cable that connects the ROV to the surface must navigate the cave's bends and passages without snagging. The vehicle must be small enough to fit through restrictions, and the operators must work without direct visual contact with the vehicle for much of the dive. The ROV was sent down through the cave's passages, past the sections accessible to divers, past the 200-metre restriction that Stanowski had pushed through the year before, and further into the void below. The cable paid out steadily. The depth readings increased. The ROV continued to descend, and the passage continued to open below it. At 404 metres, the cable ran out. The ROV stopped, not because it had reached the bottom, but because there was no more cable. The passage was still continuing below the vehicle's position. The total depth measurement from that expedition, combining the ROV's cable length with the additional line laid by Stanowski during his own dive to approximately 265 metres during the same expedition, came to 473.5 metres. This figure was confirmed as a world record for the deepest known flooded cave, surpassing Pozzo del Mero by more than 80 metres. It was announced, it was reported, and it drew the kind of attention that a world record in an unusual category tends to draw. But the number itself contains a quiet admission, one that gets lost a little in the announcement of a record. 473.5 meters is not the depth of the cave. It is the depth that was measured. The ROV did not find a floor. It ran out of cable. The passage below 404 meters was still open, still descending, still going somewhere that no instrument had yet reached. The record is real, but it is a record of how far we got, not a record of how far the cave goes, and those are two very different things. The divers who had pushed Hranice from its early modest measurements to the figures of the 2016 expedition had done something genuinely remarkable. They had, over decades of careful, incremental, dangerous work, established that a flooded cave in the Czech Republic was deeper than anything else like it on Earth, and that even after all that work, the bottom was still not in sight. As the equipment improved and the numbers grew, the cave simply kept pace, offering more depth, more passage, more darkness below the last light. It is a strange kind of exploration, one where the primary discovery is not a destination but the persistent absence of one. And with the scale of what Hranice actually represented now established on the world stage, attention turned from the history of how people had gotten this far to the harder question of what it would actually take to go further. Cave diving is, by most measures, the most unforgiving form of diving that exists. Instructors who teach it tend to say something along these lines early in training, not to frighten students away, though some do leave, but to establish a baseline of seriousness that the activity demands from the very beginning. It is not simply deep diving with a cave around it. It is a fundamentally different environment, one that removes the option that almost every other dangerous activity preserves, the ability to go up. In open water, a diver in trouble can ascend. The surface is always directly above. In a cave, the surface may be hundreds of meters of horizontal passage away, through narrow restrictions around corners, in total darkness if the lights fail. The ceiling above you is rock, and that single fact changes everything about how the activity must be approached, planned and executed. The statistics on cave diving fatalities are not easy to look up in one clean place, but the general picture has been consistent for decades. A significant proportion of cave diving deaths involve divers who entered without proper training, without proper equipment, or without the gas reserves needed to exit safely. The rule of thirds is fundamental to cave diving gas management. 1/3 of your gas supply for the journey in, 1/3 for the journey out, and 1/3 held in reserve for emergencies. Violating this rule has killed people. Running out of air in a flooded cave passage is a situation with essentially no good outcomes. There is no rescue, there is no one coming. The cave does not care. At Hranice, the challenges of cave diving are present in their standard form, and then layered with additional complications specific to this particular site. The water chemistry is one of them. The warm, geothermally influenced water at Hranice carries dissolved carbon dioxide and hydrogen sulfide in concentrations that are higher than you would find in a typical flooded cave. These dissolved gases affect visibility in ways that are not always predictable. Disturbing the sediment on the cave floor, which happens easily when a diver's fins pass close to it, can reduce visibility dramatically and quickly. In a flooded cave, losing visibility is not merely inconvenient. It means navigating by touch and by the feel of the guideline, the thin cord that connects a diver to the exit. The guideline is not a luxury in cave diving. It is the difference between finding your way out and not finding it. The dissolved gases also affect buoyancy in subtle ways. Water with high concentrations of dissolved CO2 has slightly different density characteristics than fresh or salt water, and divers at Hranice have noted that buoyancy control requires more active management than in other cave systems. This sounds like a minor technical detail, and in shallow water it would be. At 200 meters, where the margin for error is essentially non-existent, small complications accumulate into serious ones. Then there is the question of depth itself, and what depth does to the human body and mind. Nitrogen narcosis is a well-documented phenomenon. At depth, the increased partial pressure of nitrogen in a diver's breathing gas produces an effect that has been compared somewhat loosely to alcohol intoxication. Judgment becomes impaired, reactions slow. The diver may feel a sense of calm or even euphoria that is entirely disconnected from the actual situation. Narcosis typically becomes noticeable around 40 meters and increases with depth. At 100 meters, a diver breathing standard compressed air would be severely impaired. This is one of the reasons that deep cave divers do not breathe standard air. At Hranice, divers operating below roughly 60 meters use trimix, a breathing gas that combines helium, oxygen, and nitrogen in proportions calculated for the target depth. The helium replaces a portion of the nitrogen, which reduces narcosis significantly. The oxygen fraction is kept low enough to avoid oxygen toxicity, which becomes a risk at depth because the partial pressure of oxygen increases as ambient pressure increases. Getting these ratios right is not a casual calculation. Different mixes are used at different depths, and a diver on a deep expedition at Hranice may carry multiple tanks with different gas blends, switching between them at specific depths during the ascent. Managing this process correctly while navigating a flooded cave passage in low visibility is an exercise in disciplined focus that has to be practiced until it is completely automatic. The decompression requirement at Hranice depths is, for most people, difficult to fully picture. Decompression sickness occurs when a diver ascends too quickly, and dissolved nitrogen comes out of solution in the blood and tissues, forming bubbles. The consequences range from joint pain to paralysis to death, depending on severity. To avoid it, divers must ascend slowly, pausing at specific depths for specific durations to allow the gas to off-gas safely. A diver at 300 meters is not facing a brief decompression stop. They are facing something closer to a day's work on the way back up. 12 hours of staged decompression is not an extreme estimate for a deep dive at Hranice. It may be on the conservative side. During those hours, the diver is in the water in the cave managing gas supply, maintaining warmth against the cold, staying alert, and waiting. The physical and psychological endurance required for this is substantial. The cold is worth mentioning separately. The surface water at Hranice is relatively warm by cave standards, around 14 degrees Celsius, fed by geothermal springs. But temperature in caves does not remain constant with depth in the way that geothermal warming might suggest. Deeper sections of the cave are influenced by a mix of water sources, and the temperature drops in ways that are not entirely predictable. A diver spending 12 or more hours in water that is cold enough to gradually draw heat from the body, even in a dry suit, is fighting a slow and cumulative drain on physical function. Cold reduces dexterity, slows thinking, and erodes the fine motor control that precise gas management and navigation require. Cave divers at extreme depths train for this, but training for something and experiencing it at 265 meters in a flooded cave in Moravia are different things. The physical geometry of the cave adds its own layer of difficulty. Hranice is not a wide, open tunnel. It narrows in sections, sometimes to restrictions that require a diver to remove their tanks and push the equipment through separately before following. This is a maneuver that requires calm, precise technique, and the absolute certainty that what you removed and pushed ahead of you is retrievable on the other side. Doing this at depth, with cold hands, with a decompression clock running, in a cave that has no bottom yet found, is not something that can be improvised. Every movement has to be planned and rehearsed. The margin for a mistake that cannot be corrected is effectively zero. Equipment failures in this environment are in a category of their own. In most outdoor activities, equipment failure is bad, but there's usually some possibility of improvisation, assistance, or retreat. In a flooded cave at 200 meters, a failed primary light means navigating by backup lights through passages that require visual reference to navigate safely. A failed regulator at depth is a situation that, depending on what fails and how, may not be survivable. Rebreathers, which recycle exhaled gas and extend dive duration significantly, are are used by divers at Hranice for deep dives, but rebreathers have their own failure modes, some of which can be rapid and fatal. The redundancy built into a deep cave diving equipment configuration is extensive, but redundancy does not eliminate risk. It manages it partially and pushes the probability of certain failures lower without removing them from the table. There have been accidents in other deep cave systems that provide a kind of context for what the Hranice environment represents. Boesmansgat, a flooded cave in South Africa that reaches approximately 282 metres, was the site of a recovery dive in 2004 that ended in tragedy. Dave Shaw, an experienced cave diver, descended to retrieve the body of a diver who had died there the previous year. Shaw did not return. His body and a camera he had been carrying were recovered later, and the footage from that camera documented what happened in the final minutes of the dive. It is a story that the cave diving community knows well, and it is told not as a story of recklessness, but as a reminder of what can go wrong even when everything that can be prepared has been prepared. The cave did not offer a second chance. Florida's cave systems have claimed lives consistently over the decades, enough that warning signs at the entrances to some of the most popular cave diving sites have been placed there specifically because of the number of fatalities. The signs are direct. They list the ways people have died. They are not placed to be dramatic. They are placed because the information is accurate and the risk is real. Hranice is deeper than Boesmansgat, deeper than anything in Florida, deeper than any flooded cave that has been fully measured. The divers who pushed its depth record were operating in conditions where the consequences of any significant error were final. They knew this. It is not something that needs to be dramatized because it is simply the factual character of the environment. What it means is that every meter of additional depth at Hranice was earned through preparation, experience, and a particular kind of careful courage that does not look dramatic from the outside. It looks like hours of planning, careful gas calculations, equipment checks, and then a very slow descent into very dark water. The people who do this are not thrill seekers in the casual sense. Most serious cave divers are methodical, detail-oriented people who have spent years building the specific skills the environment requires. They tend to be thoughtful about risk in a way that is almost clinical. They know exactly what can kill them, and they work systematically to reduce the probability of each specific failure. This does not make them invulnerable. It makes them as prepared as preparation can make a person for something that remains genuinely dangerous no matter how well it is approached. What all of this means for Hranice is that the cave's depth is not simply a number. It is a physical barrier. Every additional meter of depth that a human being reaches in that cave represents a corresponding increase in the complexity of the dive, the gas required, the decompression time, the exposure to cold, the distance from safety. There is a depth at which human divers, regardless of preparation and equipment, simply cannot go and return. What the depth is at Hranice is not entirely clear, but the 2016 expedition with Stanowski diving to approximately 265 metres was already operating near the outer boundary of what is survivable with current technology and technique. The ROV reached 404 metres, not because a human could not be sent that far in theory, but because no human being can realistically dive to 400 metres in a flooded cave and complete the decompression required to survive the ascent. The physics of the body set a ceiling on human exploration that the cave has not yet approached from below. This is part of what makes the Hranice Abyss such a particular kind of problem. The cave has not been fully explored because it cannot be, not with a human diver. It is too deep. And the technology that might allow exploration without a human in the water, the remotely operated vehicles, the autonomous underwater vehicles, the instruments that do not need to breathe or decompress, has its own limitations in this specific geometry, as we will come to shortly. The cave sits at the intersection of two sets of limits, the limits of the human body at depth and the limits of the machines we have built to go where the body cannot. And somewhere below 473.5 metres, the passage continues, indifferent to both. The people who have gotten closest to understanding what is down there did so at considerable personal cost, and the question of how to go further is one that requires a different kind of answer than simply finding a braver diver or a stronger set of lungs. It requires rethinking from the ground up what exploration in this environment actually looks like, and who or what does the exploring. That is the question that brought the Stanowski expeditions to their particular form, and it is the question that the cave is still waiting for the world to answer. So who actually went into this cave, and how far did they get? The answer to that question has a long tail, stretching back through decades of Czech and Slovak cave diving history, through gradual pushes and incremental records, before arriving at the name and the expedition that most people associate with Hranice today. It did not happen all at once. These things rarely do. The cave gave up its depth slowly, a few meters at a time, over many years, and the people who extracted each new measurement from it did so through the kind of patient, methodical work that does not make for dramatic headlines, but is the actual texture of how exploration gets done. Czech cave divers were active in Hranice from the 1960s onward, which is earlier than many people realise. The cave was already known as unusual, already recognised as deeper than typical flooded features in the region, and the diving community in Czechoslovakia during that period was small but serious. These were not casual recreational divers. Cave diving in Central Europe in the 1960s and 1970s required a particular kind of self-sufficiency, partly because the equipment available was less sophisticated than what exists today, and partly because the knowledge base for deep cave diving was still being assembled in real time. The divers who worked Hranice in those early decades were, in a sense, figuring out the rules as they went. The initial depths reached were modest by the standards of what came later. Early divers pushed into the upper sections of the cave, reaching somewhere in the range of 40 to 60 metres, which was already a technically demanding dive given the conditions and equipment of the time. What they found was not a cave with a clear bottom and a defined shape. They found a cave that kept going. The passages continued downward past the reach of their lights, past the limit of their gas supply, past the point where it was safe to continue. They surfaced with the knowledge that the cave was deeper than they had reached, but without any clear sense of how much deeper. That uncertainty was, in its own way, the first hint of what Hranice actually was. Through the 1980s and into the 1990s, Czech speleologists and divers continued to push the known depth gradually deeper. The records moved in increments, and the cave's reputation within the Central European caving community grew. It was understood to be exceptional. The depth was accumulating in ways that were starting to become genuinely difficult to explain within the framework of normal cave formation. Flooded caves in limestone regions are not uncommon across Moravia and the broader Central European karst landscape, but none of them behaved like Hranice. None of them kept going in the way that this one did. The working assumption, for a long time, was that a bottom existed and would eventually be found. The cave was deep, yes, but surely it had a floor somewhere within reach. That assumption began to erode seriously in the 2000s. A Czech diver named Radek Hruby and his team made significant contributions during this period, pushing the known depth further and bringing more systematic documentation to the cave's upper and middle sections. The cave diving community's awareness of Hranice as something more than a regional curiosity was growing, and the site was beginning to attract attention beyond the immediate Czech and Slovak diving circles. The numbers being reported from Hranice were starting to circulate in international cave diving discussions, and the response from people who understood what those numbers meant was, broadly, a kind of quiet astonishment. It was around this time that a Polish cave diver named Krzysztof Stanowski began working at the site. Stanowski was based in the Czech Republic and had been building his cave diving experience over many years across multiple sites in Europe and beyond. He was not new to difficult caves. He had the kind of background that serious deep cave diving requires: extensive technical training, experience with mixed gases, familiarity with the specific demands of navigating flooded cave passages at depth. When he first encountered Hranice in the early 2000s, he recognised it for what it was. Not just a deep cave, but a particular kind of problem, the kind that pulls a certain type of person back repeatedly. His early dives at the site deepened his understanding of its geometry and character. The cave, as he explored it, had a personality of sorts, though that is perhaps too human a word for it. It had a structure. It had sections where the passage was wide enough to move through comfortably, and sections where it narrowed sharply, requiring divers to remove equipment and push through sideways. It had areas where the visibility was good, and the water had a strange, clean clarity, despite its mineral content, and areas where silt disturbed easily, and visibility collapsed to almost nothing. Learning the cave took time. Stanowski gave it that time. His 2015 solo dive is the one that changed the story in a meaningful way. He had been planning and preparing for it carefully, and the specific target was a narrow restriction that had been identified at around 200 meters depth. Restrictions in cave diving are exactly what they sound like. Points where the passage becomes too tight to pass through easily, where a diver must assess whether it is physically possible to get through, and critically whether it is possible to get back. Stanowski reached that restriction, assessed it, and pushed through. What he found on the other side was not another narrow passage. It was a large void. The cave opened up beyond the restriction into a space that his lights could not fully illuminate. He was floating in darkness with no visible walls on several sides, no visible floor below, the water clear and still around him. He described it afterward as one of the most striking moments of his diving career, and given his career, that carries some weight. The cave had been holding that space behind the restriction, and no one had been through to see it before. The depth below him was unknown. The passage continued downward into darkness that his equipment could not reach. He surfaced from that dive after a decompression that took many hours. He had been in the water for a very long time. He came up with the knowledge that the cave beyond the 200-meter restriction was not a dead end, not a small chamber, but something much larger and deeper, and that the depth record for Hranice was going to be revised significantly once someone could get instruments down to measure it properly. The 2016 expedition was the response to that discovery. Stanowski had connected with National Geographic, and the combination of his experience and their support made a more ambitious investigation possible. The key addition to this expedition was a remotely operated vehicle, an ROV, which could go deeper than a human diver and document what it found on camera. The ROV was deployed into the cave with a cable attached, and it descended through the passages that Stanowski and others had already mapped, through the restriction at 200 meters and into the large void beyond. The ROV reached 404 meters before the cable ran out. At that point, the operators on the surface had no more cable to pay out. The ROV was hovering in the cave passage at 404 meters depth, and the passage was still continuing below it. There was no flaw in the camera image. There was no indication that the cave was about to end. The cable was simply gone, and the ROV was at the end of its reach. Using the length of the ROV cable, an additional line that had been run into the cave, the team calculated the depth of the deepest point reached during the expedition. The figure they arrived at was 473.5 meters below the water surface. This number was subsequently verified and accepted by the relevant scientific and speleological organisations, and Hranice was confirmed as the deepest known flooded cave on Earth, surpassing the previous record holder, Pozzo del Mero in Italy, by more than 80 meters. Stanowski himself dived to approximately 265 meters during the 2016 expedition. That is a depth that places him among a very small number of people who have been that far into a flooded cave anywhere in the world. His dive was not primarily a record attempt in the sense of reaching the absolute deepest point. It was reconnaissance, documentation, and the physical act of being present in the cave to manage the ROV deployment and understand the geometry of the passages in a way that no remote instrument can fully replicate. He was in the cave while the ROV was descending below him, which is a particular kind of experience, being in a flooded cave at 265 metres, while a machine you're responsible for continues downward into darkness you cannot follow. The international attention that followed the 2016 expedition was significant for a site that had previously been known mainly within specialist communities. The combination of the National Geographic involvement, the record-breaking depth, and the striking fact that the bottom had not been found made for a story that translated well beyond the cave diving world. Here was the deepest flooded cave on Earth, and the deepest point measured was not the bottom, it was just the point where the cable ran out. That detail caught people's attention in a way that a simple depth record might not have. Within the cave diving community, the reaction was more nuanced. The record was acknowledged and respected, but the more interesting conversation was about what came next. The cave had revealed itself as something larger than anyone had confirmed before, and the question of how to explore further, given the physical limits of human diving, and the technical challenges of operating ROVs in this specific geometry, was not a simple one. The 2016 expedition had answered one question, which was how deep the cave was known to be, while opening several others, which were how deep it actually went, what was down there, and how anyone was going to find out. Starnowski has continued to be associated with the cave in the years since. His investment in Hranice is not the kind that ends with a single record. He has spoken about the cave in terms that suggest it is an ongoing project rather than a completed achievement, which makes sense given that the cave itself is ongoing in the most literal sense possible. It has not stopped. The passage continues below 473.5 metres, and the question of how far it continues is still, as of the most recent information available, unanswered. What the progression of records at Hranice shows, looked at from a distance, is something that is easy to overlook when the focus is on the final number. The cave was not discovered in 2016, and it was not revealed by a single expedition or a single diver. It was understood incrementally over decades by a series of people who each pushed a little further than the last and came back with a little more information than had existed before. The 2016 record is the current endpoint of that process, but it is not the end of the process itself. It is more like a marker on a path that is still being walked, by people who have not yet found where the path goes. The depth of 473.5 metres is the number that appears in records and articles, and it is real and verified. But it is worth being precise about what it actually represents, because the precision matters here. It is a minimum. It is the depth of the deepest point that any instrument has physically reached inside the cave. It is not the depth of the cave. The cave is deeper than that. By how much? No one currently knows. And that distinction between the deepest point reached and the actual depth of the cave is what makes the story of Hranice something other than a simple record-breaking narrative. It is the story of a place that has so far declined to give up its full extent, and the question of what is down there, below the end of the cable, below the reach of any human diver, is one that the cave is still holding on to. What that means scientifically, and what tools might eventually provide the answer, is where the story goes next. So let us stay with that number for a moment. 473.5 metres. It is worth understanding exactly what it is and what it is not, because those are two different things, and the difference between them is the whole point. The measurement was taken from the water surface, the surface of the lake you can see when you stand at the edge of the Hranice Abyss and look down at the turquoise green water below you. From that surface down to the deepest point that the ROV line physically reached inside the cave, the distance is 473.5 metres. That is what was measured. That is what was verified. The line went down, the ROV descended along the passage, and at 473.5 metres, the cable was exhausted. The ROV stopped. The camera was still running, and below the ROV the passage continued. There was no flaw in the image. Not a flaw that was close, not a flaw that was visible in the distance. Just the passage, open, descending further into the dark. The ROV did not reach the end of the cave, it reached the end of its cable, which is a very different thing, and so the number 473.5 meters is, technically speaking, a lower bound. A minimum, the cave is at least that deep. How much deeper it goes is something the measurement cannot tell us, because the measurement stopped before the cave did. This distinction is not a minor technical footnote, it is the central fact about Hranice. The record is real, the measurement is accurate, but what the record describes is the deepest point any instrument has reached, not the deepest point of the cave itself. The cave is deeper than 473.5 meters. We just do not know by how much. To put the scale of this in some context, it helps to look at the previous record holder. Before the 2016 Hranice measurement was confirmed, the deepest known flooded cave on Earth was Pozzo del Mero, a flooded sinkhole located in the Lazio region of Italy, not far from Rome. Pozzo del Mero had been measured at 392 meters. It is also a flooded sinkhole in limestone, also formed by geological processes rather than surface erosion, and it held the world record for a number of years. It is a genuinely impressive sight. 392 meters of flooded cave is not something to minimize. Hranice surpassed it by more than 80 meters of confirmed depth. 80 meters is not a marginal improvement. If you stacked a 20-story building on top of another 20-story building, you would be getting close to 80 meters of height. The difference between the previous world record and the confirmed depth at Hranice is roughly that. And then, beyond the confirmed depth at Hranice, the cave continues further still. Pozzo del Mero has been measured. Its bottom is known. Hranice has not been measured to its bottom because no instrument has reached its bottom. So the comparison is between a cave with a known depth of 392 meters and a cave with a known minimum depth of 473.5 meters, the actual total depth of which is unknown. What is also worth noting is that the Pozzo del Mero record had stood for a long time before Hranice overtook it. The cave diving and speleological community had considered Pozzo del Mero the benchmark, and when Hranice surpassed it so significantly, and did so while still leaving the bottom unconfirmed, it shifted the conversation about what the deepest flooded cave in the world might eventually turn out to be. The record at Hranice is not a stable endpoint. It is a snapshot of the deepest point reached so far in a cave that has given no indication of being close to finished. There is another way to think about the depth, and it involves what is happening above the cave rather than inside it. The town of Hranice sits in the Moravian landscape, at an elevation of roughly 240 meters above sea level. The water surface of the lake in the cave is slightly below the town's general level, but in the same rough range. This means that the bottom of the cave, or at least the deepest confirmed point, extends to somewhere around 230 meters below sea level, and possibly considerably further. The cave is not just going down through rock, it is going down through rock that is already below the level of the sea. Whatever is at the bottom of Hranice, or below the bottom that has been measured, exists in a geological layer that is significantly below sea level, which gives you a sense of how far the hypogenic water processes have carved through the limestone over millions of years. The question of what the true depth might be is one that scientists have approached not just through direct measurement, but through inference. The geothermal water that feeds the cave rises from somewhere below. The chemistry of that water carries information about where it has been, how long it has travelled, and how deep its source is. And when researchers began analysing that chemistry carefully, the picture that emerged was one that suggested the cave's connection to underground water systems goes considerably deeper than 473.5 meters. Isotope analysis of the water, examining the specific ratios of different forms of hydrogen and oxygen atoms in the water molecules, can give scientists information about the temperature and pressure conditions the water experienced before reaching the surface. The water at Hranice carries signatures consistent with water that has been in contact with rock at significant depth and elevated temperature. Some estimates based on this kind of analysis suggest the water originates from depths of potentially 1,000 meters or more below the surface. This does not necessarily mean the cave itself extends 1,000 meters down. The water may travel through rock fractures and porous zones that are not open cave passages. But it does suggest that the underground water system feeding Hranice has roots that go far deeper than the passages we have managed to reach. The geophysical surveys that have been conducted at the site add another layer to this picture. Czech and international geologists have used seismic and gravity measurement techniques to look for void spaces in the rock below and around the cave. These methods work by detecting subtle variations in how seismic waves travel through rock, or in local gravitational pull, which can indicate the presence of large empty or water-filled spaces. The results of these surveys have detected anomalies below the confirmed depth of 473.5 meters. What exactly those anomalies represent, whether they are connected passages, large chambers, or simply zones of fractured and porous limestone, is difficult to determine from surface measurements alone. But they suggest that the cave system does not simply terminate at the point where the ROV cable ran out. The cave, in other words, is almost certainly larger than what has been documented, by how much is genuinely uncertain. The honest answer is that nobody knows, and the tools available so far have not been able to give a precise figure. The 473.5 meter number is solid. Everything below it is inference, estimate, and geological suggestion. There is something a little vertiginous about this, if you let yourself think about it. Most record-breaking things are records of something fully measured. The tallest building, the longest river, the deepest ocean trench. These are numbers attached to things that have been measured from one end to the other. The Mariana Trench is about 11,000 meters deep, and we know that because instruments have reached the bottom and come back with the measurement. Hranice is different. The record is a record of the deepest point reached, not the deepest point that exists. It is a record of human and technological reach, not of the cave's actual extent. The cave's actual extent is still unknown. That is a genuinely unusual situation for a world record to be in. It also means that the record is, in principle, breakable without Hranice getting any deeper. If someone develops an ROV with a longer cable, or an autonomous vehicle that can navigate the cave's geometry and reach a point further down, the confirmed depth number will increase, not because the cave changed, but because the instrument reached further. And if that instrument also does not find the bottom, the record will again be a minimum, a new lower bound on a depth that remains unconfirmed. This could go on for some time. There is a slightly strange quality to this, and it is worth acknowledging. In most exploration contexts, the goal is to find the thing, the bottom of the canyon, the far shore of the lake, the summit of the mountain. At Hranice, every expedition so far has not found the thing. They have found a new limit of their own reach, and beyond that limit, the cave continues. It is a little like trying to measure a room in the dark by walking across it, and every time you think you must be near the far wall, you take another step and there is still floor beneath you. Except the room is a flooded cave in the Czech Republic, and the walk is a technically complex ROV deployment at hundreds of meters depth. What is also interesting is that the record, even as a minimum depth, is significant enough to matter scientifically. The fact that a flooded cave in Central Europe is known to extend at least 473.5 meters below the water surface tells geologists something real about the hypogenic karst processes that formed it. It tells them that these processes, given the right conditions, the right rock, the right chemistry, the right geological history, can carve passages to depths that are genuinely remarkable. The depth at Hranice is not just a number for a record book. It is data about what geological processes can do over millions of years, and that data informs how scientists think about similar formations elsewhere in the world. It also raises a practical question that the cave diving and exploration community has been wrestling with since the 2016 expedition. If the confirmed depth is 473.5 meters, and the cave continues below that, What would it take to push the measurement further? The ROV that reached 404 metres before the cable ran out was operating at the limit of its design. Getting deeper requires either a longer cable, which introduces its own complications in terms of weight, drag, and the difficulty of managing a tether through narrow cave passages, or a different kind of vehicle entirely, one that does not depend on a tether at all. Both options exist in principle, neither is simple in practice, and the cave's specific geometry, the narrow sections, the sharp turns, the passages that require precise navigation to avoid snagging equipment, makes the problem harder than it would be in open water. The depth record then sits where it has sat since 2016, 473.5 metres, verified, accepted, real. And below it, the cave continues, patient and indifferent, holding whatever is down there in the dark and the warm geothermal water, waiting for an instrument with enough reach to finally find out how far it goes. To understand what scientists think might actually be down there, what the water chemistry and the geological surveys are pointing toward, it helps to look more closely at the science that has been done without anyone needing to go inside the cave at all. The geophysical surveys conducted at and around Hranice are worth spending a moment on, because they represent a genuinely different approach to the problem. When you cannot send a person or a machine deep enough to measure something directly, you try to read it from the outside. This is the logic behind surface geophysics, using instruments on or near the ground to detect what is happening in the rock below, without ever entering the rock itself. At Hranice, Czech and international geologists have used two main methods. The first is seismic surveying, which works by sending sound waves into the ground and recording how they reflect and refract as they pass through different materials. Rock, water, and empty space all respond to seismic waves differently. A large void filled with water, for example, will return a different signal than solid limestone, and a trained geophysicist can read those differences in the data and draw inferences about what is down there. The second method is gravity surveying, which is more subtle but in some ways more telling. The gravitational pull of the Earth at any given point on the surface is slightly influenced by the density of the material beneath. Dense rock pulls slightly harder than empty space or water-filled cavities. By taking very precise gravity measurements across the surface above the cave, researchers can detect anomalies, places where the pull is slightly weaker than expected, and use those anomalies to map regions of lower density underground. It is a slow, painstaking kind of work, and the resolution is not fine enough to draw a precise map of cave passages. But it can tell you, with reasonable confidence, that something is there. The results of these surveys at Hranice have been consistent in one important way. They suggest that the cave system continues below the confirmed depth. The anomalies detected in the gravity data point to void or low-density zones extending below 473.5 metres, which is already where the ROV cable ran out. The exact geometry of those zones is hard to determine from the surface. It could be a continuation of the main shaft, or it could be a network of smaller connected passages, or some combination of both. But the signal is there, and it is not consistent with the cave simply stopping at the point where human instruments have so far reached. This is not proof of how deep the cave goes. It is more like a geological suggestion, a reading of something that does not quite add up if you assume the cave ends where the measurement ended. The water chemistry tells a related but different story, and in some ways it is the more compelling one. The water inside the Hranice Abyss is not ordinary groundwater. It is a mixture, and the two components of that mixture come from very different places. The cooler, fresher component infiltrates from the surface. Rainwater and snowmelt that percolates down through the limestone over months or years, picking up minerals along the way. That part is not unusual. Many cave systems receive water this way. What is unusual at Hranice is the other component, geothermal water that rises from significant depth, carrying a chemical signature that is distinctly different from anything that has been near the surface recently. This geothermal water is warmer, more mineral-rich, and carries elevated concentrations of carbon dioxide and hydrogen sulfide. The carbon dioxide is particularly important because it is the carbon dioxide dissolved in rising water that drives the hypergenic dissolution process, the acid from below mechanism that carved the cave in the first place. The hydrogen sulfide adds another layer of acidity when it oxidizes in contact with oxygen-bearing water, producing sulfuric acid, which is extraordinarily effective at dissolving limestone. This is the same chemistry that formed Lechuguilla Cave in New Mexico and Movel Cave in Romania, both famous for their unusual geology and, in Movel's case, their completely isolated ecosystems. The presence of this chemistry at Hranice means that the cave is not just a relic of past processes. The dissolution is to some degree still happening. The cave is still being carved slowly by the same mechanism that created it. That is a strange thing to sit with. The cave is not finished. It is an ongoing geological event. Researchers have used isotope analysis to try to determine where the geothermal water originates. Isotopes are variants of chemical elements with slightly different atomic masses, and the specific isotopic ratios in a water sample can act like a fingerprint, pointing toward the temperature and depth at which the water last equilibrated with the surrounding rock. The isotopic signatures in the Hranice water suggest that the geothermal component has travelled through rock at considerable depth and temperature before rising into the cave system. Some analyses have pointed towards source depths potentially on the order of 1,000 meters or more below the surface. That figure carries significant uncertainty. Isotope geochemistry is not a GPS for groundwater, and the interpretation involves assumptions that may or may not hold precisely in this particular geological context. But the direction of the signal is clear. The water rising into Hranice has come from somewhere very deep, and it has been on a long journey through hot rock before arriving in the cave. This has an important implication for thinking about the cave's extent. If water is rising from a source potentially 1,000 or more meters below the surface, and if that water is dissolving rock as it rises, then the cave passage through which it travels could, in principle, extend to depths approaching that source. The cave would need a conduit, a connected system of passages, linking the surface lake to the deep geothermal water source. Whether such a conduit exists as a single continuous shaft or as a more complex network of fractures and passages is unknown, but the water has to get from somewhere to somewhere, and the chemistry suggests that somewhere is very deep. The cave is in a sense the visible evidence of that journey. What is not yet visible is how much of that journey is accessible or even mappable with current tools. The researchers involved in this scientific work have been careful not to overclaim. The teams from Masaryk University in Brno, the Czech Geological Survey, and the Czech Speleological Society have published findings that are measured and qualified. They do not say the cave is 1,000 meters deep. They say the data is consistent with a cave system that extends significantly beyond the confirmed depth, and that the geothermal water source is likely located at considerable depth below the current measurement. These are careful scientific statements, not dramatic declarations, and they are the right kind of statements to make when working with indirect evidence. The honest position is that the geophysical and geochemical data point in a consistent direction, but direct measurement, an instrument that actually reaches the bottom, is the only thing that would confirm it. What is also worth noting is the carbon dioxide concentration in the water. Dissolved CO2 in cave water is not unusual, but the concentrations at Hranice are elevated, and they vary with depth in ways that reflect the mixing of the two water sources. Near the surface, where the cooler infiltration water dominates, the CO2 is lower. Deeper, where the geothermal component becomes more significant, the CO2 increases. This gradient is one of the reasons that diving in Hranice is chemically different from diving in a typical freshwater cave. The water is mildly fizzy, in a way that is perceptible to divers, and the dissolved gases affect buoyancy in subtle ways that require adjustment. It is also a reminder that the cave is a chemically active environment, not a static one. The sulfur is detectable even at the surface. People who have visited the site describe a faint but distinct smell, not overwhelming, not unpleasant in small doses, but unmistakably there. It is the same quality that you notice near hot springs or volcanic vents, a faint mineral sharpness in the air. At the surface of the lake, this is mild. The water is warm to the touch, around 14 degrees Celsius near the top, which is noticeably warmer than most Czech groundwater, which tends to run between 8 and 10 degrees. This warmth was what drew people to the site in the 19th century, when the mineral water was bottled and sold for its supposed medicinal properties, and when the spa resort was built nearby. The warmth is real, and it does come from the Earth's interior, just not in the way the Victorian-era spa visitors were probably imagining. They were drinking geothermally heated water that had dissolved its way up through hundreds, or possibly thousands of meters of Devonian limestone. It was not a health cure, but it was genuinely unusual water with a genuinely unusual origin. The ongoing chemical activity of the cave also means that the cave walls are not static. Dissolution is happening slowly at the contact between the rising geothermal water and the limestone. The cave is, in a very real sense, getting slightly larger over time, not in any way that would be noticeable on a human timescale. The rate of dissolution is measured in geological time, millimeters per century or slower. But the process is not over. The same mechanism that has been carving this cave for millions of years is still operating. The cave is not a finished object. It is a process. And that process has no particular reason to stop at 473.5 meters or at any other depth that happens to correspond to the length of an ROV cable. There is something that the science keeps circling back to, which is the question of connection. Does the Hranice Abyss connect, somewhere below the confirmed depth, to a larger underground water system? The geothermal water has to come from somewhere, and it has to travel through some pathway to reach the cave. That pathway might be the cave itself, a continuous shaft or series of passages linking the surface to the deep source. Or it might be a network of fractures and microchannels too small to navigate, which feed water into the cave from many directions. Distinguishing between these possibilities from the surface is difficult. The geophysical data can suggest the presence of large voids, but it cannot resolve the fine structure of a fracture network. To know whether Hranice connects to a broader underground system, you would need to either trace the water directly, using chemical tracers injected at one point and detected at another, or send an instrument deep enough to observe the passage geometry firsthand. Tracer studies have been conducted in the broader Moravian karst region, using dye injection to track water movement between surface points and cave systems. These studies have helped map some of the regional groundwater flow, but the deep geothermal component of Hranice is difficult to trace in the same way, because its source is too deep and too distant to inject dye into practically. The tracer approach works well for surface-fed water, moving through relatively shallow karst. For water rising from a kilometre below the surface, the logistics become essentially impossible with current methods, so the science sits in a particular position, strongly suggestive, carefully qualified, and genuinely uncertain about the most important question. The geophysical surveys say there is more cave below the confirmed depth. The water chemistry says the water is coming from somewhere very deep. The isotope data suggests that somewhere could be on the order of 1,000 meters below the surface. But none of these lines of evidence individually or together can say with precision how deep the cave actually goes, or what its geometry looks like below 473.5 meters. That answer is still waiting for an instrument with enough reach to go and find it. What the science has done, though, is change how researchers think about the cave. Before the geophysical surveys and the detailed water chemistry work, it was possible to imagine that the cave might simply be a very deep shaft that happened to extend further than expected before terminating in a sealed chamber or a collapsed passage. The scientific picture that has emerged makes that seem less likely. The cave is geologically active. The water rising through it comes from great depth. The surface surveys detect anomalies well below the current confirmed depth. Taken together, these suggest a cave system that is still connected to deep geological processes, still being shaped by them, and potentially extending much further than the current measurement captures. That is not a comfortable conclusion if you're hoping for a tidy answer, but it is an honest one, and it sets up a question that goes beyond the depth record itself, because a cave that is still biologically and chemically active, still connected to deep geothermal processes, still being dissolved from below, is not just an interesting geological feature, it is also a potential habitat. And what lives in a place like that, in the warm, sulphurous, mineral-rich water below the reach of any diver or instrument so far, is a question that the biologists have been thinking about just as carefully as the geologists. So let us think about that question for a moment, because it is a genuinely strange one. We are talking about a flooded cave in the Czech Republic, a landlocked country in Central Europe, nowhere near a tropical reef or a deep-sea vent, and we're asking whether something might be living in its deepest water, something that has never seen sunlight, never needed it, and may not even be aware that sunlight exists as a concept. That sounds like the setup for a science fiction story. But the biology of places like Hranice has a way of making science fiction feel slightly underdressed. The water in the Hranice Abyss is not empty. That much is clear from what researchers have been able to examine in the upper sections, the parts that divers can actually reach. The warm, mineral-rich, slightly sulphurous water that fills the cave is, from a biological standpoint, not a dead zone. It is a chemical environment. And wherever there is a chemical environment with enough energy available, life tends to find a way to use it. The organisms that have been documented in the accessible portions of the cave are, in some cases, familiar. Small crustaceans, invertebrates, the kinds of creatures you might find in other cave water systems across Europe. Cave-adapted species often lose pigmentation over time, since colour serves no purpose in permanent darkness, and they frequently develop enhanced sensory organs to compensate for the absence of vision. Some cave crustaceans have elongated antennae that are almost comically long relative to their body size, essentially converting their entire surface area into a detection instrument. These adaptations take thousands of generations to develop, which tells you something about how long organisms have been living in places like this. But the more interesting biology at Hranice is not the crustaceans, it is the microbes. Chemosynthetic bacteria have been identified in the cave water. These are organisms that do not photosynthesize. They do not use sunlight to convert carbon dioxide into organic matter the way plants do, because there is no sunlight to use. Instead, they derive energy from chemical reactions, specifically from the oxidation of compounds like hydrogen sulfide and iron, which are present in the geothermal water rising through the cave. This process is called chemosynthesis, and it is the metabolic foundation of some of the most unusual ecosystems on Earth. The most famous examples of chemosynthetic ecosystems are the hydrothermal vent communities discovered in the deep ocean in the late 1970s. Before those discoveries, the scientific consensus was that all life on Earth ultimately depended on sunlight, either directly or indirectly. Every food chain, the thinking went, traced back to a plant or an alga that had captured solar energy. The vent communities broke that assumption completely. Tube worms, clams, shrimp, crabs, entire ecosystems thriving in complete darkness at the bottom of the ocean, supported entirely by bacteria that were eating the chemistry of the water rather than the energy of the sun. It was a genuinely paradigm-shifting discovery, and it opened up questions about where else this kind of life might exist that scientists are still working through today. The chemosynthetic bacteria in the Hranice Abyss are doing something similar on a smaller scale in a very different setting. The hydrogen sulfide and carbon dioxide in the cave water are not just geological curiosities, they are food sources, in the same way that sunlight is a food source at the surface. The bacteria oxidize these compounds, releasing energy, and use that energy to build organic molecules. Those organic molecules can then in principle support other organisms that feed on the bacteria. A food chain, in other words, built entirely on the chemistry of the Earth's interior, with no connection to the surface world at all. This is not unique to Hranice. The most extensively studied example of a sealed, chemosynthesis-based cave ecosystem is Movil Cave in Romania, discovered in 1986 near the Black Sea coast. Movil Cave had been sealed from the surface for an estimated 5 million years. The water inside it is warm, sulphurous, and rich in dissolved gases, not entirely unlike Hranice. When researchers finally entered it, they found 48 species that exist nowhere else on Earth. Spiders, leeches, water scorpions, isopods, all adapted to a world with no light and no surface food input. The entire ecosystem was running on chemosynthesis, supported by microbial mats of sulfur-oxidizing bacteria floating on the water surface inside the cave. 48 unique species in a cave that nobody knew existed until 38 years ago. Hranice is not Movil Cave. It is not sealed, and it is not isolated in the same way. The upper sections connect to the surface lake, which connects to the broader environment. But the deeper sections, the parts below the diver accessible zone, the parts below the end of the ROV cable, are a different matter. Down there, the conditions are increasingly dominated by the geothermal water rising from depth. The influence of the surface world decreases with depth, and the influence of the Earth's interior increases. Whatever lives in that water, if anything does, is living in an environment that has more in common with a hydrothermal vent than with a typical European cave. No biological samples have been collected from below the diver accessible zone at Hranice. This is simply a function of access. Nobody has been able to get a sample container to those depths and bring it back. The ROV in 2016 was not equipped for biological sampling. Its purpose was depth measurement and visual documentation. So the biological picture of the deep Hranice water is, at the moment, entirely inferential. The conditions suggest that chemosynthetic life could exist there. The water chemistry provides the necessary chemical energy. The temperature is elevated, which generally favours microbial activity. There is no reason, based on what we know about extremophil biology, to assume the deep water is sterile. But inference is not the same as observation, and the biologists are careful about this. It is possible that the deep water at Hranice is biologically sparse, or even nearly empty, if some condition that is not yet understood makes it inhospitable. The concentration of dissolved gases might be too high for even extremophile organisms. The pressure at depth, roughly 47 atmospheres at 473 meters, is significant, though many deep-sea organisms handle comparable or greater pressures without difficulty. The specific chemistry of the water might favour some organisms and exclude others in ways that are not yet predictable. The honest answer is that we do not know what is down there, and we will not know until someone finds a way to collect a sample from it. What we do know is that the question is worth asking seriously. The history of cave biology is full of cases where a cave that seemed unlikely to harbour significant life turned out to contain something genuinely surprising. Movil Cave is the most dramatic example, but it is not the only one. Lechuguilla Cave in New Mexico, which shares the hypogenic formation mechanism with Hranice, has been found to contain microbial communities living inside the rock itself, not in the water or on the cave floor, but embedded in the limestone, deriving energy from the minerals in the rock. These are called endolithic organisms, and they represent a mode of life so slow and so minimal that it barely registers as life by intuitive standards. Some endolithic microbes divide once every 1,000 years. They are not thriving in any conventional sense, but they are alive, and they are doing something, and they have been doing it for a very long time. The possibility of similar organisms in the walls of the Hranice Abyss, at depths far below the current confirmed measurement, is not far-fetched. It is the kind of possibility that makes the cave interesting to biologists in a way that goes beyond the depth record. The depth record is remarkable, but it is ultimately a number. The biology is a different kind of question, one that touches on the boundaries of what life is and where it can exist. There is also something worth noting about what the biology of Hranice, even in the accessible upper sections, tells us about the connectivity of the cave. The organisms living in the cave water did not appear from nowhere. They arrived somehow, whether through the surface lake, through groundwater connections, or through very slow dispersal over geological time. Tracing the genetic relationships between cave organisms and their surface relatives can sometimes reveal how long a cave population has been isolated and through what pathways it arrived. This kind of genetic analysis has been applied to Moville cave fauna with interesting results, and there is no reason it could not be applied to Hranice organisms as well. Whether it has been done systematically is not entirely clear from the available literature, but it is the kind of work that a motivated research team could undertake without needing to go anywhere near the dangerous lower sections of the cave. The microbial mats are perhaps the most visually striking biological feature of the accessible cave sections. These are communities of bacteria and other microorganisms that grow on the cave walls and on submerged surfaces, forming visible films or patches that can look almost like a thin coating of paint in certain lighting. They are not decorative. They are the base of the food chain, the organisms doing the chemical work that makes the rest of the ecosystem possible. In caves with active geothermal water, these mats can be surprisingly extensive, covering large areas of the cave wall in a thin but continuous layer. Whether similar mats exist in the deeper sections of Hranice is unknown, but the chemistry of the water strongly suggests that the conditions for them are present. One thing that the biology of the cave reinforces, in a slightly roundabout way, is the point the geologists have been making about the cave's continued activity. A biologically active cave is not a sealed, static system. It is a place where chemical energy is being processed, where organic matter is being produced and consumed, where the water chemistry is being continuously modified by living processes as well as geological ones. The organisms in the cave are not just passengers in a geological feature. They are participants in its chemistry, in a small but real way. The sulfur-oxidizing bacteria, for instance, produce sulfuric acid as a byproduct of their metabolism. Sulfuric acid dissolves limestone, so the bacteria are, in a very modest sense, contributing to the dissolution of the cave walls, adding their own tiny increment to the geological process that has been carving the cave for millions of years. Life and geology, in other words, are not entirely separate things here. They are intertwined in the way that they often are in places where the Earth's interior and the surface world are in close contact. This is part of what makes Hranice genuinely interesting to a range of different scientific disciplines. It is not just a cave diving record. It is not just a geological curiosity. It is a place where geophysics, geochemistry, hydrology, microbiology, and cave biology all have something to say, and where the answers to questions in one field tend to open up questions in another. The depth record got the headlines in 2016, and reasonably so. It is a concrete, dramatic fact that is easy to communicate. But the researchers who work on the cave are often more interested in the questions that the depth record raises than in the record itself. How deep does it actually go? Where is the water coming from? What is living in the water we cannot reach? How is the cave still changing? These are the questions that keep the scientific interest alive, and they are questions that a deeper ROV dive, or a biological sampling expedition, or a new geophysical survey could potentially begin to answer. For now, though, the biology of the deep Hranice water remains in the category of informed speculation, supported by everything we know about similar environments, but not yet confirmed by direct observation. That gap between what the conditions suggest and what direct evidence can confirm is, in a way, a precise description of the situation at Hranice more broadly. The cave keeps offering evidence of its own depth and complexity, and keeps withholding the final answer, and the tools that might provide that answer are, as it happens, exactly what the next part of this story is about. The remotely operated vehicle that went into Hranice in 2016 was not a piece of exotic, purpose-built machinery designed specifically for flooded caves. It was a fairly standard ROV of the kind used in underwater research and industrial inspection. A compact thruster-driven unit with lights, cameras, and a spool of cable connecting it to operators at the surface. In open water, this kind of vehicle is highly capable. It can maneuver freely, maintain position, and relay high-quality video while the cable hangs loosely in the water behind it. In a flooded cave, almost none of those advantages apply in the same way. The cable is the central problem. An ROV in open water can pay out cable in a more or less straight line behind it, or in a gentle arc. In a cave, the cable must follow the same route the vehicle takes, through passages, around corners, past sections where the walls close in. Every bend in the passage adds friction to the cable. Every narrow section is a potential snag point. If the cable catches on a rock ledge and the ROV continues forward, the tension builds until either the cable pulls free or the ROV is dragged backward or something breaks. In a cave system with the geometry of Hranice, narrow in sections opening into larger voids, with walls that are not smooth but irregular and fractured, managing the cable is not a secondary concern. It is one of the primary engineering challenges of the entire operation. The team working the 2016 ROV had to think carefully about how the cable was routed through the upper sections of the cave before the vehicle even reached the deeper parts. Divers physically guided the cable through certain passages, positioning it to minimize contact with the walls and reduce the risk of snagging. This is painstaking work, and it takes time. The ROV's effective range is not simply determined by how much cable is on the spool. It is determined by how much cable can be safely deployed through the specific geometry of the cave without losing control of the vehicle. At Hranice, that geometry imposed real limits. When the ROV reached 404 meters and the cable ran out, it was not a failure of the equipment in any simple sense. The vehicle was functioning, the cameras were working, the lights were on. There was simply no more cable. The decision about how much cable to bring had been made before the expedition, based on the best available information about the cave's depth, which at that point was not yet confirmed to exceed 400 meters. The ROV reached its limit in a passage that continued downward. That is the honest summary of what happened. And it is also the reason that 473.5 meters is a minimum, not a total. The 473.5 meter figure itself was arrived at through a combination of the ROV's cable length, an additional line deployed by Stanowski and the dive team. It represents the deepest point physically reached during the expedition, confirmed by measurement. Below that point the passage continued, and the cave has not been measured since. The number is real and verified, but it has an asterisk attached to it that is larger than the number itself. Sonar has been tried as an alternative approach, sending acoustic pulses into the cave and measuring the return time to estimate distances and map void spaces. In open water, sonar is a reliable tool. In a narrow, irregular cave passage, it becomes much less precise. Sound bounces off walls in multiple directions. The geometry of the passage distorts the return signal. The results can give a general sense of whether a large void is present beyond a certain point, but they cannot produce the kind of detailed depth measurement that a physical line or cable can provide. At Hranice, sonar surveys have contributed to the broader understanding of the cave's extent, but they have not resolved the question of how deep it actually goes. They have, if anything, reinforced the impression that there is more cave below the current measurement than the measurement itself suggests. The most promising alternative to a tethered ROV, in terms of technology, is an autonomous underwater vehicle, an AUV. The distinction matters. An ROV is connected to its operators by a cable and is controlled in real time. An AUV carries its own power source, its own sensors, and its own navigation system, and operates independently. It does not need a tether. In theory, an AUV could descend into Hranice, navigate through the passages under its own guidance, collect data and return to the surface without any cable management problem at all. The depth limitations imposed by a finite spool of cable would not apply. In practice, the challenges are significant. AUVs designed for open water research are typically not small enough to navigate cave passages. They are built for ocean surveys, pipeline inspection in relatively open conditions, or shipwreck documentation where the vehicle can maneuver around the outside of a structure rather than through its interior. A vehicle designed to fit through the narrow sections of Hranice, some of which require human divers to remove their tanks and push through sideways, would need to be quite compact. Compact means limited battery capacity, limited sensor payload, and limited computational resources for navigation. Navigation is its own problem. AUVs in open water typically use a combination of GPS at the surface, acoustic positioning, and inertial navigation to track their location. Inside a cave, GPS is unavailable. Acoustic positioning becomes unreliable for the same reasons sonar mapping does, and inertial navigation accumulates error over time. A vehicle navigating through a complex three-dimensional cave passage for several hundred meters of vertical depth would need very good inertial navigation and some way of correcting its position estimate as it goes. The technology for this exists in various forms, but integrating it into a vehicle small enough to fit through Hranice's tighter passages is not a trivial engineering task. There have been discussions within the cave diving and speleological research communities about designing or adapting AUVs for exactly this kind of environment. The interest is real. Cave exploration is not the only application. There are industrial and military uses for small autonomous vehicles that can navigate confined underwater spaces, and some of the engineering work being done for those purposes is directly relevant. But as of the most recent publicly available information about Hranice, no AUV expedition has been mounted. The discussions remain at the level of proposals and feasibility assessments, not funded projects. Cost is a persistent constraint. The 2016 expedition had National Geographic support, which made it possible in a way that a purely academic or volunteer effort could not have been. Mounting a new ROV expedition with a longer cable, or developing and deploying an AUV, would require significant funding. The cave is scientifically interesting, but it is not the kind of high-profile, politically visible project that attracts large government grants. It sits in a somewhat awkward position, too specialised and remote for mainstream science funding, and not quite dramatic enough on an ongoing basis to sustain continuous media attention after the initial 2016 record was announced. The researchers and divers who care about it most are often working with limited budgets and considerable personal commitment. There is also the question of the cave's physical geometry changing with depth. The sections that human divers have reached are by definition sections that a human body can fit through. The sections below the diver accessible zone may be more open, or they may be tighter, or they may alternate between the two. The ROV footage from 2016 showed a passage continuing downward beyond the cable's reach, which suggests the cave does not simply pinch off at that point, but the detailed geometry of what lies below 473.5 meters is genuinely unknown. Designing a vehicle to navigate that geometry requires either knowing the geometry in advance, which is circular, or designing a vehicle flexible enough to handle a range of possible passage sizes and shapes. One approach that has been used in other deep cave surveys is to send down a small camera on a weighted line, essentially a very simple instrument that can at least confirm whether a passage continues and give some visual information about what it looks like. This is far less capable than an ROV or AUV, but it's also far cheaper and simpler. Whether this has been attempted at Hranice below the 473.5 metre mark is not clear from the available record. It is the kind of low-cost first step that might at least confirm whether the passage remains open for a further significant distance. What any new technology deployment at Hranice would ideally accomplish is not just a new depth number, though that would be significant. A properly instrumented vehicle could collect water samples from the deepest accessible point, measure temperature and pressure precisely at depth, document the geological features of the cave walls, and potentially detect biological material, organic compounds, microbial DNA, suspended in the water column. Each of those data types would contribute to a different scientific question. The water samples would inform the hydrology and the biology. The temperature measurements would help refine the geothermal models. The geological documentation would help with understanding the cave's formation and its likely future trajectory. The depth number would be the headline, but the scientific value would be in everything else. It is worth pausing on the temperature question for a moment, because it is slightly counterintuitive. The surface water at Hranice is warm, around 14 degrees Celsius, which is noticeably warmer than most Central European surface water. This warmth comes from the geothermal springs feeding the cave, but as you descend into the cave, the water does not simply get warmer the deeper you go, as you might expect if you were thinking of it as a geothermal gradient. The situation is more complicated, because the cave water is a mixture of different sources, the warm geothermal water rising from depth and cooler water infiltrating from the surface. The mixing happens at various depths, and the temperature profile of the water column reflects that mixing in ways that are not entirely predictable without direct measurement. Divers who have descended into the cave have reported that the water cools noticeably below the warm surface layer, which is the opposite of what a simple geothermal story would suggest. Getting precise temperature measurements at depth would help researchers understand the mixing dynamics and, by extension, the flow pathways of the water, where it is coming from and where it is going. The protected status of the cave adds another layer of complexity to any future expedition planning. Hranice Abyss is designated as a natural monument in the Czech Republic, which means that access and any scientific or exploratory activity requires permits and oversight. This is appropriate. The cave is irreplaceable, and unregulated access could damage it. But it also means that mounting an expedition involves a regulatory process in addition to the technical and financial challenges. The Czech Speleological Society and relevant government bodies are involved in managing access, and any new major expedition would need to work within that framework. This is not an insurmountable obstacle, but it is part of the real-world context in which further exploration of the cave would have to happen. The cave diving community's interest in Hranice has not faded since 2016. It remains one of the most discussed sites in technical cave diving circles precisely because it is unfinished. Most famous cave diving destinations have been explored to a reasonably definitive conclusion, their passages mapped, their depths measured, their features documented. Hranice has not reached that conclusion. It is still, in the most literal sense, an open question. For divers and researchers who are drawn to that kind of open question, it has a persistent pull. There is something almost frustrating about the situation, in the best possible way. The cave is accessible. It is in the Czech Republic, not at the bottom of the ocean or in the middle of an uninhabited continent. It has been visited by researchers and divers for decades. It is a protected and monitored site. And yet the most basic fact about it, how deep it is, remains unknown. The technology to find out probably exists, or could be assembled from existing components. The knowledge and expertise to conduct the expedition certainly exists. What has been missing, so far, is the specific combination of funding, equipment, and logistical coordination needed to push past the current limit. That combination will almost certainly come together at some point. The cave is too interesting and the question too concrete for it to remain permanently unanswered. When it does, when a new expedition goes in with a longer cable, or a purpose-built AUV, or some instrument configuration not yet assembled, the result will either be a new depth number, or the discovery that the cave bottom is within reach, or the confirmation that the passage continues so far beyond current measurement that the question simply becomes larger. Any of those outcomes would be significant, and the person most likely to be involved in whatever comes next if past involvement is any guide, is the same diver who has been returning to this cave for more than 2 decades, drawn back each time by the same dark water and the same unanswered question at the end of his line. His story, and what the cave has actually felt like from the inside, is where this account goes next. Krzysztof Stanowski is not the kind of person who tends to dominate a room. By most accounts, he is quiet, methodical, precise. The sort of diver who spends more time checking his equipment than talking about it. He is Polish by birth, but has spent much of his adult life based in the Czech Republic, which is part of why Hranice became his cave rather than someone else's. Geography and habit brought him there first. What kept him coming back was something harder to explain. He first encountered the Hranice Abyss in the early 2000s, and his initial impression, like that of most divers who arrive expecting something dramatic, was probably a mild version of confusion. The surface lake is small. The water is warm and slightly cloudy near the top. The opening does not announce itself as the entrance to anything record-breaking. It looks like a flooded quarry, which in some ways it resembles, even though it is entirely natural. Stanowski began diving it the way cave divers approach new sites, carefully, incrementally, mapping what was there and noting where the passage went. He was not the first person to dive Hranice. Czech divers had been going in since the 1960s, but he became the person most systematically committed to understanding how far it went. Through the 2000s, he made repeated dives, pushing deeper each time as his experience and equipment allowed. Cave diving at depth is not a sport where you simply decide to go further and then go further. Each significant depth increase requires planning that can take months. Calculating gas mixes, staging cylinders at various depths for decompression, understanding the passage geometry, preparing for the specific failure modes that become more likely the deeper you go. A diver at 200 meters in a flooded cave is not having an adventure in the casual sense of the word. They are executing a carefully engineered procedure in an environment that will not forgive significant errors. Stanowski understood this, and his progression through the cave reflected it. He moved deeper by increments that were large enough to matter, but not so large as to be reckless. The 2015 solo dive is the one that changed the nature of the exploration. By that point, Stanowski had pushed past the depths, reached by previous divers, and was working in territory that no human had entered before. At around 200 meters, roughly equivalent to the height of a 60-story building, measured downward through water, he encountered a restriction. This is a common feature in cave systems, a narrowing of the passage where the rock closes in and the diver must pass through a gap that may be barely wider than their body and equipment. Restrictions are one of the things that make cave diving genuinely dangerous, because they require the diver to remove tanks, push them through separately, and then reassemble their equipment on the other side, all while managing buoyancy and gas supply in a confined space. At 200 meters, doing this alone, the margin for error is essentially zero. He passed through, and on the other side of that restriction, the cave opened. He has described what he found in terms that are worth sitting with for a moment. The passage widened into a void, a large dark space that his lights could not fully illuminate. Cave diving lights are powerful, but they have a finite range, and a space large enough to exceed that range in multiple directions gives the diver no sense of walls or ceiling or floor. Stanowski floated in the middle of this space and could not see the edges of it. The water was clear. Hypogenic cave water tends to be clearer than surface-fed cave water because it does not carry the sediment and organic material that rainwater picks up on its way down. Clear water in a large underground space with powerful lights should give you good visibility. But visibility and comprehension are different things. You can see clearly for 20 meters in every direction and still not know how large the space is, because beyond those 20 meters there is only darkness. He has used the word indifferent to describe the feeling of being in that space. Not hostile, not welcoming, just completely indifferent to his presence. The cave did not care that he was there. It had been there for millions of years before him, and would be there for millions of years after him, and his lights and his bubbles and his careful breathing were a temporary and entirely irrelevant interruption of its normal state. which was darkness and silence, and the slow movement of mineral-laden water. There is something philosophically interesting about that description, and also something that is simply accurate. A cave at 200 meters is not performing for you. It is not doing anything for you at all. You are just briefly inside it. The physical reality of a dive at that depth is worth understanding, because it is easy to imagine cave diving as something like snorkeling with better equipment, and it is not that at all. The equipment Stanowski was using for the 2015 dive would have included a rebreather, a closed-circuit breathing system that recycles exhaled gas rather than venting bubbles, which extends gas supply dramatically and is essentially required for dives of this duration and depth. The gas mix at that depth would be tree mix, a combination of helium, oxygen, and nitrogen, because breathing standard compressed air at 200 meters would cause nitrogen narcosis severe enough to be incapacitating, and oxygen toxicity that could cause seizures. Helium reduces both of these risks, but it also changes the way sound travels through the breathing gas, giving the diver's voice a characteristic high pitch that is the least of its effects. The suit would be a dry suit, providing thermal insulation against water that cools significantly below the warm geothermal layer near the surface. The equipment load, tanks, rebreather, bailout cylinders, lights, line reels, instruments, would be substantial. Moving through a restriction while managing all of this, alone, at 200 meters, in a cave no one else was in, is a specific kind of experience that very few people on Earth have had. After passing through the restriction and spending time in the void beyond it, Stanowski had to come back up, and coming back up from 200 meters in a flooded cave is not a quick process. Decompression is the body's requirement to off-gas the inert gases, primarily helium and nitrogen, that have dissolved into the blood and tissues under pressure. If a diver ascends too quickly, those gases form bubbles in the body, causing decompression sickness, which ranges from joint pain to paralysis to death depending on severity. The required decompression stops on the way up from 200 meters in a cave like Hranice would have taken many hours. Stanowski spent most of a day in the water after that dive, ascending slowly, stopping at prescribed depths for prescribed durations, hanging in the water column in the dim light of the cave while his body slowly equilibrated to lower pressure. That is a long time to be alone in a flooded cave thinking about what you just saw. He has said that the cave does not feel threatening during the decompression stops. The water is warm near the surface, and the upper sections of the cave are familiar by now. He has spent enough time in them that they feel known. But the psychological dimension of cave diving at this level is real and worth acknowledging. You're in a place where, if something goes wrong, no one can reach you in time to help. The nearest person is on the surface, which is many hours of careful decompression away. Your safety depends entirely on your equipment and your own judgment, and both of those things have finite reliability. Most experienced cave divers develop a particular kind of focused calm that is not the absence of awareness, but rather the management of it. You know the risks, you have prepared for them as thoroughly as possible, and you proceed anyway because the preparation has been thorough enough that you trust it. Whether that calm ever fully extends to a solo dive at 200 meters in the deepest known flooded cave on Earth is a question only Stanowski can answer. The 2016 expedition changed the scale of what was happening at Hranice. National Geographic's involvement brought funding, equipment, and international attention that the cave had not previously received. Stanowski was the central diver, but the expedition was a larger operation: surface support, equipment logistics, the ROV deployment that would produce the 473.5 meter measurement. His own dive during the 2016 expedition reached approximately 265 meters, which was itself a record for the site and for flooded cave diving in general at that time. The ROV went deeper than any human had gone, but Stanowski went deeper than any human had gone before, and what he found at that depth was more passage, more cave continuing downward, with no indication of a floor. He has described the experience of being at that depth as one of complete quiet. Not silence exactly. The rebreather makes sounds, the equipment makes sounds, the diver's own breathing is audible, but a quality of quiet that is different from anything on the surface. There is no ambient noise from the world above, no wind, no traffic, no other people, no weather. The sounds are only the sounds you brought with you. And below those sounds is a stillness that has probably not been disturbed since the last time geothermal water shifted through the rock. That quality of stillness, he has suggested, is part of what draws him back. It is not comfortable exactly, but it is very complete. There is nothing else there except the cave and the question. The question being, how far does it go? What is striking about Stanowski's relationship with Hranice, when you look at it across 2 decades, is how much of it has been about patience rather than conquest. He did not arrive and immediately push for the deepest possible dive. He built his understanding of the cave incrementally over years, returning again and again, going a little deeper each time as the preparation warranted it. This is how serious cave diving works, not through bravado but through accumulation of knowledge and experience. Each dive taught him something about the cave's geometry, its water conditions, its particular challenges. By the time he made the 2015 solo dive, he knew the cave well enough that the unknown part, the void beyond the restriction, was a calculated extension of what he already understood, not a leap into complete ignorance. He has also been clear, in interviews and accounts of the expeditions, that he does not think of himself as competing with the cave or trying to defeat it. The framing of exploration as conquest, of reaching the bottom as winning something, does not seem to fit how he thinks about it. The cave is not an opponent, it is a place, with a physical reality that is independent of anyone's desire to measure it. What he wants, as far as can be understood from his public statements, is simply to know what is there. The scientific questions interest him. The depth record is a consequence of the exploration, not the goal of it. Whether that framing is entirely accurate or partly a useful narrative is impossible to say from the outside, but it is consistent with how he has described the work over many years. The partnership with National Geographic gave the 2016 expedition a profile that brought Hranice to the attention of people who had never heard of it, which is most people, since flooded cave depth records are not generally front-page news. The footage from the expedition, including the ROV's descent into the dark water, was striking enough to communicate something of what the cave actually is. Watching a remotely operated vehicle descend through clear green water, past limestone walls, into increasing darkness, with the depth counter climbing past 100, 200, 300, 400 meters and still not finding a flaw. That is a reasonably effective way of conveying the scale of the place to someone who has never thought about it before. Stanowski has continued to be associated with Hranice since 2016. He is, at this point, the person who knows the cave better than anyone else alive. He has spent more time in it, at greater depths, than any other human being. If another major expedition is organised, with a longer tether ROV or an AUV or some new configuration of equipment, his involvement would be expected. He's not a young diver anymore, but depth record cave diving is not a young person's sport in the way that some extreme activities are. It rewards experience and judgment over physical youth, and Stanowski has accumulated more relevant experience at Hranice than anyone else could have. What he has not been able to answer after all of it is the central question. He has been deeper in this cave than any other person. He has floated in a void that his lights could not fully illuminate, at a depth that would have seemed impossible to earlier generations of divers. He has spent cumulative days suspended in its water, ascending slowly through its passages, watching the light from the surface gradually grow above him. And he still does not know where the bottom is. He is not sure there is a bottom within reach of current technology. The cave simply continues below the deepest point he has reached, as it continued below the deepest point the ROV reached, as it has continued below every limit that has been placed on it so far. That is an unusual situation to be in, to know a place intimately, its smells, its temperatures, its passages, its particular quality of darkness, and still not know its most basic dimension. It is a little like spending years in a house and never finding out how many rooms it has, except that the rooms keep going down and the stairs never end. Stanowski has described the cave as having a pull that is difficult to articulate. He keeps going back not because he expects the answer on the next dive, but because the question is still there, and the cave is still there, and the combination of the two has not released its hold on him. That quality, the persistent, patient pull of an unanswered question, is probably the most human thing about the whole story. The geology is extraordinary, and the depth record is impressive, and the biology is genuinely surprising. But the thing that makes it feel like a story rather than just a data set is the fact that a person has been returning to this cave for 20 years, going deeper each time, and still has not reached the end of it. And somewhere below the deepest point he has reached, the cave continues, dark, warm, indifferent, and entirely unconcerned with the question of whether anyone will ever find its floor. When you compare Hranice to the other deep flooded caves of the world, the specifics of what makes it unusual start to come into focus in ways that go beyond the depth number alone. Pozzo del Mero is probably the most natural point of comparison. It sits in the Lazio region of Italy, not far from Rome, and for many years it held the title that Hranice now holds. Its depth is confirmed at 392 metres, measured properly, with a floor identified. It is also a flooded sinkhole in limestone, also formed in conditions that produced unusually deep vertical development, and it is also the kind of place that looks, from the surface, like it should not be as significant as it is. A circular pool of blue water in Italian countryside surrounded by rock, attracting the occasional technical diver and the occasional curious geologist. The difference is that Pozzo del Mero has a bottom. Divers have been there. The number 392 metres is a complete measurement, not a minimum. When Hranice surpassed it in 2016, the margin was not small. 473.5 metres is more than 80 metres deeper, and that 473.5 is, again, only the depth to which the ROV cable reached before running out. The actual depth of Hranice is greater than that by an unknown amount, so the comparison between the two is not really between 392 and 473.5. It is between 392 and something larger than 473.5, with the upper end of that range still undetermined. That is a meaningful distinction. Pozzo del Mero is a remarkable place. Hranice is a remarkable place that has not yet been fully understood. Boesmansgat in South Africa is a different kind of comparison, and it carries a heavier weight because of what happened there. The cave, whose name translates roughly as Bushman's Hole, reaches a confirmed depth of 282.6 metres. It is an inland flooded cave in the Northern Cape, in an arid landscape, and it became the site of one of the most discussed events in cave diving history. In 2004, a diver named Dave Shaw descended to 270 metres and discovered the body of Dion Dreyer, a South African diver who had died in the cave in 1994. Shaw returned in January 2005 with the intention of recovering the body. He did not come back. His own body, and Dreyer's, were eventually recovered by a support team. Shaw's death was captured on his helmet camera, and the footage was later analysed in detail. It is a story that people in the cave diving community know well, and it is a reminder that the depth records associated with these places are not just numbers. They are the outer edges of what is survivable with current equipment and physiology. Boesmansgat is shallower than Hranice by almost 200 metres. Shaw died at 270 metres. The implications of that for what it would mean to explore Hranice's deeper sections are not comfortable to sit with for too long. Zacaton in Mexico is a closer geological parallel than either Pozzo del Mero or Boesmansgat. It is a cenote, a flooded sinkhole, in the state of Tamaulipas, and it was formed by the same hypogenic process that created Hranice. Acidic, geothermally heated water rising from below and dissolving limestone upward over geological time. Its depth is approximately 335 metres, which made it for a period the deepest known flooded sinkhole in the world. It is also the site of an early robotic exploration. In 1993, a NASA-funded autonomous underwater vehicle called Depth X was deployed at Zachaton as part of research into how robotic explorers might one day operate in the subsurface oceans of places like Europa. The vehicle mapped the cave in 3 dimensions and collected water samples from depth. Zachaton, in other words, has already been explored by a robot without a tether. The fact that this was done in the 1990s in Mexico and has not yet been replicated at Hranice in the Czech Republic says something about the complicated relationship between scientific interest, funding, and logistics that governs these projects. The geological similarity between Zachaton and Hranice is worth holding on to. Both were formed by the same upward dissolving mechanism. Both have geothermally influenced water. Both have produced depths that surprised researchers. The difference is that Zachaton has a measured floor and Hranice does not. The Blue Hole of Dahab in Egypt is worth mentioning simply because it is the flooded cave that most people have actually heard of, and the contrast with Hranice is instructive. Dahab's Blue Hole is a coastal sinkhole in the Red Sea, off the Sinai Peninsula, and it reaches a depth of roughly 130 metres. It is famous partly for its beauty. The water is extraordinarily clear and blue, the coral is vivid, the setting is dramatic, and partly because it has claimed a disproportionate number of lives, earning a reputation as one of the most dangerous dive sites in the world. But 130 metres is not particularly deep by the standards of what we have been discussing. It is less than a third of the confirmed minimum depth of Hranice. The Blue Hole is famous because it is accessible, visually striking, and located in a place that attracts recreational and technical divers from around the world. Hranice is not famous in the same way, despite being significantly deeper and scientifically more interesting. This is partly a matter of geography. The Czech Republic is not a dive destination in the way that Egypt's Red Sea coast is, and partly a matter of the kind of exploration involved. You cannot snorkel over Hranice and appreciate it visually the way you can hover above Dahab's Blue Hole in clear sunlit water. Most of what makes Hranice extraordinary is invisible from the surface and inaccessible without extremely specialised equipment. What the comparisons with other deep flooded caves actually reveal, when you look at them together, is that Hranice occupies a genuinely unusual position. It is not simply the deepest of a set of similar things. It has specific characteristics that set it apart even within the category of deep hypogenic flooded caves. The first is location. Central Europe is not where you would expect to find the deepest flooded cave on Earth. The Moravian landscape around Hranice is pleasant, green, and historically inhabited. It is a region of small towns, agricultural land, and managed forests. The kind of extreme geological feature that the Hranice Abyss represents seems more at home in a remote desert, or a tropical forest, or the floor of the ocean. Finding it in a place where people have been building spas and taking medicinal baths since the 19th century is genuinely strange. The cave was not discovered in some distant wilderness by an expedition that spent weeks reaching it. It is a short drive from a moderately sized Czech city, in a landscape that has been domesticated for centuries. The fact that it hid its true depth for so long in such an ordinary-seeming setting is part of what makes it interesting. The second distinguishing characteristic is the geological activity. Hranice is not a relic. It is not a cave that formed under conditions that no longer exist and has been sitting unchanged since then. The geothermal water that created it is still flowing. The chemical processes that dissolve the rock are still occurring. The cave is still being shaped right now at depths that no one has reached. This is different from many of the world's famous cave systems, which are essentially finished products, formed under ancient conditions and now static, gradually filling with formations or slowly collapsing, but not actively growing. Hranice is still growing. The bottom, wherever it is not fixed. It is moving slowly downward as the acidic water continues its patient work on the limestone below. This makes the cave a living geological system in a way that most caves are not, and it means that the scientific questions it raises are not just historical, they are questions about processes that are happening right now. The third characteristic is the one that has been central to everything discussed so far, the absence of a confirmed bottom. Every other deep flooded cave that holds or has held a depth record has been measured. Divers or robots have reached the floor, confirmed it, and returned with a number. Hranice has not been measured. The 473.5 meters is a floor on the depth, not a ceiling. The cave continues below that point, and by how much is genuinely unknown. Geophysical surveys suggest significant void space below the deepest measured point. Water chemistry suggests the geothermal source is far deeper than 473.5 meters. The cave's own geometry, as described by Stanowski in the ROV footage, shows passages continuing downward without sign of closure. There is no scientific basis for assuming the cave ends anywhere near the current record. It could be 500 meters deep. It could be 600. Some estimates, based on the isotopic signatures of the water, suggest the system could extend to depths of 1 kilometer or more. These are estimates, not measurements, and they should be treated with appropriate caution. But the point is that no one has a good reason to think the bottom is close. The cave has consistently produced more depth than anyone expected at every stage of its exploration, and there is no obvious reason to assume that pattern has ended. This combination, unexpected location, active geology, and unmeasured depth, is what makes Hranice genuinely different from the other caves it is most often compared to. Pozzo del Mero is deeper than most flooded caves but has a flaw. Zacaton shares the hypogenic origin, but has been mapped. Bozeman's Gad is famous for its tragedy but is shallower. The Blue Hole of Dahab is famous for its beauty but is in a different category of depth entirely. Hranice sits alone in the position of being the deepest confirmed flooded cave on Earth and still not being fully understood. That is an unusual thing for a geological feature to be in the 21st century, when satellite imaging can map the surface of the planet in extraordinary detail and sonar has charted most of the ocean floor. The fact that there is a hole in the ground in the Czech Republic, in a place people have been visiting for leisure for over a century, that goes deeper than any other known flooded cave and has not yet been fully measured. That is, when you stop to think about it, a genuinely remarkable situation. There is also something worth noting about the community of people who have explored these caves. The world of extreme deep cave diving is small. The number of people who have the training, experience and equipment to dive at 300 meters or more in a flooded cave is not large. These divers know each other, follow each other's work and are aware of each other's records. When Stanowski pushed past the depth of Pozzo del Mero, it was not an anonymous achievement. It was noticed by a community that understood exactly what it meant and exactly how difficult it was. The same names appear across multiple sites. Divers who have worked at Bozeman's Ghat have connections to divers who have worked at other deep sites. The records at each cave exist in a shared context of knowledge about what the human body and available equipment can do at extreme depth in confined spaces. Hranice is part of that shared context, but it occupies a particular position within it, the site that has not yet given up its full measurement, the cave that keeps returning a larger number than the last attempt. What all of these comparisons ultimately circle back to is the question of what it means for a place to be truly known. Pozzo del Mero is known, its depth is measured, its floor has been visited, its geometry is mapped. Bozeman's Ghat is known in a different way, its depth is confirmed, but it is also known through tragedy, through the specific weight of what happened there in 2005. Zacaton is known through robotic exploration, through the three-dimensional maps produced by DepthX. The Blue Hole of Dahab is known through the experience of thousands of divers who have descended into its blue water over the decades. Hranice is not yet fully known in any of these ways, Its upper sections are known, divers have been there, the walls and passages are familiar to those who have explored them. But below the level that human divers have reached, and below the level that the ROV cable reached, the cave is unknown in a fairly complete sense. Not mysterious in a vague or poetic way, but literally unmeasured and unvisited. The water is there, the rock is there, the passages presumably continue, but no instrument and no person has been there to confirm what the specific reality looks like. That gap between what is known and what is not is exactly what keeps the scientific interest in Hranice alive. It is not a closed case. It is an open question with a physical location you can visit, stand beside and look into, and the answer is still somewhere below the surface, unreachable with current means, waiting for the next attempt. And what that next attempt might look like, and what it might finally reveal, is where the story of Hranice goes from here. So the question becomes a practical one. What does the next attempt actually look like, and what would it take to make it happen? The Czech Speleological Society continues to monitor the Hranice Abyss. That monitoring is ongoing and relatively quiet. It does not involve dramatic expeditions every year, but rather the steady, careful work of scientists and surveyors who track the cave's water chemistry, temperature, and physical condition over time. This kind of long-term observation is genuinely valuable. It builds a baseline. It allows researchers to notice changes, shifts in water temperature, variations in dissolved gas concentrations, subtle alterations in flow patterns that might indicate something is happening deeper in the system. The cave is not being ignored between expeditions. It is being watched carefully and patiently by people who understand that a geological feature this unusual deserves sustained attention, even when no one is actively descending into it. But monitoring is different from exploration, and the gap between what is currently known and what remains unknown at Hranice is not going to be closed by water chemistry readings alone. At some point, something will need to go deeper, either a person or a machine or both. The most straightforward path would be another ROV expedition with a longer cable. The 2016 expedition ran out of tether at 404 metres. The confirmed depth of 473.5 metres incorporated the ROV's reach plus additional line paid out from the surface. A vehicle with significantly more cable could, in theory, go deeper. The challenge is not just the cable length itself, though that matters. The challenge is managing that cable through the cave's geometry. Hranice is not a straight vertical shaft. It has bends, restrictions, and irregular passages. Every metre of cable that passes through a narrow section or around a corner is a potential snag point, a place where friction builds up and control degrades. Operating a tethered vehicle in that environment requires careful planning, experienced operators, and a very clear understanding of the cave's internal structure before the vehicle goes in. You cannot simply lower a longer cable and hope for the best. There have been proposals, discussed among researchers and cave diving communities, for deploying a new ROV with a significantly extended tether, purpose-designed for the specific challenges of the Hranice passages. These proposals exist at the level of planning and conversation rather than funded scheduled operations, at least based on what has been publicly reported. The funding question is real and not trivial. A serious deep cave ROV expedition with custom equipment, a skilled technical team, surface support infrastructure, and the logistical complexity of working at a protected natural monument in the Czech Republic is not a cheap undertaking. The 2016 National Geographic expedition brought significant resources to the project, and the combination of a major media partner and the world record result created conditions that are not automatically repeatable. Getting that level of support again requires a compelling reason, and while the cave is still scientifically fascinating, the argument for funding becomes more nuanced when the question is not whether it is the deepest, but how much deeper it might be. This is a common tension in scientific exploration of this kind. The first record is the headline. The confirmation of the record and the attempt to fully measure what was discovered is quieter work. It matters just as much scientifically, arguably more, but it does not generate the same public attention. Researchers who work on Hranice are aware of this. The cave's status as a protected natural monument adds another layer. Access is regulated, and any expedition requires permits and coordination with Czech authorities. That is not an obstacle in a negative sense. The protection is appropriate for a site of this significance. But it does mean that exploration cannot happen casually or quickly. The other technological path being discussed in relevant research communities involves autonomous underwater vehicles, AUVs. These are underwater robots that operate without a tether. They carry their own power, their own sensors, and their own navigation systems, and they move through the water independently, following pre-programmed routes or making decisions in real time based on sensor data. The advantage over a tethered ROV is obvious. No cable to manage, no snagging, no cable length limitation. An AUV could, in theory, descend through the full depth of the Hranice system without the logistical complications that a tether creates. The practical challenges are significant though. AUVs designed for open water or ocean environments are often too large to fit through the narrow sections of a flooded cave. The geometry of Hranice, the same geometry that makes tether management so difficult, also constrains the size and shape of any vehicle that needs to pass through it. There is active development of smaller, more manoeuvrable AUVs for applications like pipeline inspection and shipwreck exploration in confined spaces, and some of that work is directly relevant to the cave diving context. Vehicles being designed to navigate the interior of a sunken ship or a narrow industrial conduit face similar geometric constraints to those encountered in a flooded cave passage. The technology is advancing, and it is not unreasonable to think that within the next decade or two, an AUV capable of operating in the Hranice environment could exist. The other requirement for an AUV is that it must come back. Unlike a tethered ROV that can be hauled to the surface if something goes wrong, an autonomous vehicle that loses power or gets stuck in a narrow passage is simply lost. The vehicle itself is expensive. More importantly, if it gets lodged in a passage, it could complicate or block future access to the deeper sections of the cave. Any AUV deployment at Hranice would need extremely high confidence in the vehicle's reliability and its ability to navigate back through the passages it descended. That confidence requires detailed prior knowledge of the cave's internal geometry, which is itself still incomplete below the levels reached by human divers. There is also the question of what sensors such a vehicle would carry. Depth measurement is the obvious goal, but the scientific value of a deep Hranice expedition goes well beyond confirming a number. Water sampling at depth would be enormously valuable. Collecting water from below 473.5 meters and bringing it to the surface for analysis could reveal biological material, isotopic signatures, dissolved gas concentrations, and temperature profiles that are not accessible by any other means. A vehicle capable of collecting water samples at multiple depths during a single descent would answer questions that geophysical surveys conducted from the surface simply cannot. The water itself carries information about where it came from, how long it has been underground, and what it has passed through on its way up, and that information is currently sitting below the reach of any instrument that has been deployed. Finding the bottom, if there is a definable bottom which is not guaranteed, would accomplish several things at once. It would allow a complete depth measurement, replacing the current minimum figure with an actual confirmed number. It would allow the cave's total geometry to be mapped, at least in broad terms, giving geologists a clearer picture of the void space and how it relates to the surrounding rock. It would confirm whether the cave terminates in a floor or whether it connects to a larger underground water system that extends beyond any single measurable point. That last question is particularly interesting. Some hypogenic cave systems connect to extensive underground networks, The water that rises through them is part of a larger hydrological system that moves through rock over vast distances and depths. If Hranice connects to such a system, the relevant geology is not just the cave itself, but a much larger underground structure that the cave is simply the most accessible part of. Water sampling from depth would also give biologists something to work with. The upper sections of the cave have yielded chemosynthetic bacteria and small invertebrates, but below the level accessible to divers, the biology is completely unknown. It is possible that nothing lives at the greatest depths. The conditions may be too extreme, the dissolved gas concentrations too high, the pressure too great. But it's also possible that organisms adapted to those specific conditions exist there, just as organisms have been found in environments that once seemed incompatible with life. The only way to know is to collect samples, and the only way to collect samples is to get something down there that can bring material back up. The cave is, as mentioned, a protected natural monument under Czech law. This status reflects a genuine recognition of the site's scientific and geological significance, and it means that any future exploration will happen within a framework of oversight and regulation. That is appropriate. A site like Hranice, if left unprotected, could be damaged by unregulated diving or by commercial interests. The protection ensures that the cave remains available for serious scientific work and that access is managed carefully. It also means that future expeditions will need to demonstrate their scientific value and their commitment to preserving the site's condition. Not an unreasonable bar, but one that requires planning and coordination. The scientific interest in Hranice is genuine and sustained, even if the funding and logistics of deep exploration remain challenging. Researchers at Masaryk University in Brno, the Czech Speleological Society, and affiliated institutions continue to study the cave's water chemistry and geology. International collaborators with expertise in hypogenic karst systems, deep cave biology, and underwater robotics are aware of the site and its open questions. The cave exists within a scientific community that understands what it represents and what answering its remaining questions would contribute. That community is not large, and the resources available to it are modest relative to the scale of the problem, but the interest is real and the work continues. There is something worth noting about the pace at which this kind of science moves. The 2016 expedition was a significant leap. It established the world record, deployed the ROV, and brought international attention to the site. Since then, the next major step has not yet happened. That gap might seem surprising given how dramatic the 2016 findings were. But this is actually fairly normal in deep cave exploration. The preparation required for a serious attempt is enormous. The funding is difficult to secure, and the window of conditions, weather, water levels, equipment availability, team availability, that makes an expedition feasible is narrow. The gap between major milestones at sites like this is often measured in years, sometimes in decades. The cave is patient. It has been there for hundreds of millions of years. It will wait. What finding the bottom would mean, in a broader sense, is worth thinking about for a moment. It would not close the story of Hranice entirely. A confirmed depth would open new questions about how the cave formed, what its connection to deeper geological systems looks like, and what lives in its deepest water. Scientific answers tend to generate more questions than they resolve, but it would provide a foundation. Right now, the cave is defined by its minimum depth and its open-endedness, by the fact that the number is a floor, not a total. A confirmed measurement would change that. It would give geologists a fixed point from which to work, a number to compare against the geophysical surveys and the isotopic models, a physical reality to anchor the theoretical estimates. That kind of grounding matters in science. Speculation is useful when it points toward investigation, but investigation is what actually moves understanding forward. For the people who have dedicated years to Hranice, Stanowski, the Czech speleologists, the researchers analysing the water chemistry, The question of the bottom is both scientific and personal. It is the thing the cave has not yet given up. Every other piece of information has been gathered through patience and ingenuity. The depth record, the water analysis, the geophysical surveys, the biological samples from the upper sections. But the deepest point remains unvisited and unmeasured, and that incompleteness sits with the people who know the cave best as an unfinished thing. Not in a way that is frustrating exactly, more in the way that an open question is always present in the background, acknowledged, considered, returned to when conditions allow, not forgotten. The next attempt will come. The specific form it takes, a longer tether ROV, a new generation of AUV, a human diver with equipment that does not yet exist in its final form, is not yet determined. What is determined is that the cave is still there, still geologically active, still dissolving slowly downward through Devonian limestone that has been in place for nearly 400 million years. The water is still rising from depth, still carrying its dissolved gases and its geothermal warmth, still doing the slow chemical work that has made this place what it is. The passages that the ROV's camera showed continuing downward past the end of the cable are still there, still dark, still unvisited. And somewhere below 473.5 metres, by how much, no one yet knows, the cave continues. That is the situation as it stands. Not a mystery in the dramatic sense, not a puzzle with a hidden answer waiting to be revealed by the right key. Just an open question in a flooded cave in Moravia, in a place that looks like a quiet lake from above, where the water smells faintly of sulphur and the surface reflects the limestone cliffs and the sky, and where the depth below that surface is still, in the most literal sense, unknown. Before we close tonight, there is one more thing worth sitting with, something that the depth records and the geology and the technology all circle around without quite saying directly. Something about what this cave, specifically, represents in the broader picture of what we know and do not know about the planet we live on. Think about where you're sitting right now, or lying down maybe. Think about the ground beneath you, the floor, the foundation, the soil below that, and then the rock. Most of us do not think about the rock. It is just there, solid and assumed, the thing everything else rests on. We build on it, we tunnel through it occasionally, we extract things from it when we need to, but we do not, as a general habit, think about how deep it goes, or what might be inside it, or what processes are still quietly happening within it at this very moment, far below anything we could reach. That is what the Hranice Abyss makes you think about if you let it. Not in a frightening way, more in the way that looking at a very old tree makes you think about time, not with dread, but with a kind of quiet recalibration. A reminder that the world has been doing things for much longer than we have been watching, and that our maps and measurements, however careful, are still partial. There is a lake in Moravia. It sits in a valley near the town of Hranice, in the Olomouc region of the Czech Republic. The water is green and slightly warm. The limestone cliffs around it are pale and weathered. If you visited on a calm afternoon, you might sit at the edge and watch the water and think it was pleasant. Peaceful even. The kind of place that gets a paragraph in a regional travel guide. The kind of place where, in the 19th century, people came to take the waters, to soak in the mineral warmth of it, to breathe the slightly sulphurous air, to rest. And below the surface of that quiet lake, there is a flooded cave that descends at least 473.5 metres into the earth, and then continues further. By how much, no one knows. That number, 473.5 metres, is worth holding for a moment, because it is easy to hear it and let it pass without really feeling what it means. The Eiffel Tower is about 330 metres tall. The Empire State Building to its roof is about 443 metres. The confirmed depth of the Hranice Abyss is deeper than either of those structures is tall, measured straight down from a surface that looks, from above, like an ordinary lake. And the cave does not end there. The ROV ran out of cable. The passage continued. The measurement is a minimum, not a total. We have been visiting this place for spa treatment since the 1800s. The warm mineral water was bottled and sold, people with aching joints soaked in it. And the whole time, beneath their feet, this thing was there. This extraordinary geological structure, this open-ended shaft in Devonian limestone, this place where geothermally heated water rises from depths that isotopic analysis suggests might be 1,000 meters or more below the surface, dissolving rock as it goes, slowly and without pause, in a process that has been running for millions of years. There is something almost funny about that, in a gentle way. The cave was not hiding exactly. It was right there. The water was warm and fizzy, and it smelled of sulphur, and people drank it for their health. The signs were all visible. But the full picture of what was below did not become clear until people started going in with tanks and lights and eventually a robot on a cable. And even now, after all of that, the picture is still incomplete. This is what the Hranice Abyss is, at its core. Not a mystery in the sense of something concealed or strange or inexplicable. It is simply a place that the Earth made over an enormous span of time, using processes that are well understood in general terms, but that produced, in this specific location, something that exceeds our current ability to fully measure. The geology is not mysterious. Hypogenic karst formation, the dissolving of limestone by acidic water rising from depth, is documented and studied. The same mechanism shaped Lichugila Cave in New Mexico, and the sulfur caves of Romania, and the cenotes of Mexico's Yucatan. We know how it works, we just did not expect it to produce something quite this deep, quite this close to the surface, in quite this location. Central Europe is not where you expect to find the deepest flooded cave on Earth. That expectation is itself worth examining. We tend to imagine the great unknowns of the planet as being in remote places, deep ocean trenches, polar ice sheets, dense tropical rainforests, and there are genuine unknowns in all of those places. But the Hranice Abyss is a reminder that the geography of the unknown does not always follow our intuitions. A flooded cave in Moravia, a place with a functioning train station, and a spa resort and a history of human habitation going back centuries, turned out to contain something that no one has yet reached the bottom of. That is not nothing. That is actually quite a significant fact about the world. It also says something about the relationship between familiarity and knowledge. We assume that familiar places are known places. A lake you can see, a valley you can walk through, a town with a name on a map. These feel known, and in many senses they are. The surface of the Hranice area is well documented. The geology of the region has been studied. The history of the spa is recorded. But familiarity with the surface of a place is not the same as knowledge of what lies beneath it, and the Hranice Abyss demonstrates that gap very clearly. The surface was familiar for a long time before the depth was understood, and the depth is still not fully understood now. Krzysztof Starnowski, the Polish cave diver who has spent more time inside Hranice than perhaps anyone else, described floating in a void at around 200 meters, a space he could not see the edges of, the water clear, the darkness extending beyond his lights in every direction, including downward. He could not see a floor. He could not see walls on all sides. He was suspended in a geological structure that had no visible boundary from where he was, and he had gotten there by swimming through passages in a flooded cave, and he would need to spend many hours decompressing on his way back to the surface. That is a remarkable thing to have experienced. And what it points to is not just the depth of the cave, but the fact that there are still places on this planet where a human being, even with significant preparation and equipment, encounters something genuinely unknown. Not metaphorically unknown, literally, physically unmeasured and unvisited. We talk sometimes about exploration as if it is a historical category, something that happened in the age of sailing ships and hand-drawn maps, something that ended when the last blank spaces on the surface of the Earth were filled in. But the Hranice Abyss is a reminder that exploration is not over. It has just moved into different dimensions, downward, mostly, into the deep ocean, into the deep cave systems, into the subsurface water networks that connect geological structures across distances we're only beginning to trace. The tools are different now. ROVs and trimix gas and isotope analysis instead of sextants and chronometers, but the basic situation is the same. There are places we have not yet reached, and we are working on reaching them, and the process is slow and expensive and sometimes dangerous and always incomplete. The people doing this work are not famous for the most part. Stanowski became known in cave diving circles and got a National Geographic expedition out of it, which is more visibility than most cave explorers receive. The Czech speleologists and the researchers at Masaryk University and the geologists running seismic surveys over the site are doing their work largely outside of public attention. This is normal for science. Most of it happens quietly, in specialised journals and conference presentations and field notebooks, and the broader world only notices when something reaches the scale of a world record or a dramatic discovery. The Hranice Abyss reached that scale in 2016 and got some attention, and then the attention moved on, as it does, while the cave itself continued to exist, unchanged, waiting. That patience, the patience of the cave, of the geology, of the people who study it, is one of the things that stays with you when you think about this place. The Devonian limestone that forms the walls of Hranice was laid down in a shallow tropical sea approximately 380 to 400 million years ago. The hypergenic processes that began carving the cave started long after that, but still millions of years before anything resembling a human being existed on this planet. The cave has been forming slowly and continuously through timescales that make the entire history of human civilization look like a brief afternoon, and it is still forming. The water is still rising, the rock is still dissolving, the cave is still, in a very real sense, under construction. Against that backdrop, the fact that we have been aware of this place for a few centuries and have been seriously measuring it for a few decades is a very small thing. We arrived recently, we looked down, we sent a robot as far as the cable would reach, and we found that the cable was not long enough. That is where we are. It is not a failure. It is simply the current state of a very young inquiry into a very old place. There is a version of this story that would end on a note of grand mystery, with dramatic music and a suggestion that the depths of Hranice conceal something extraordinary, something that will change everything when we finally reach it. That version would be dishonest. The honest version is quieter. What is down there is almost certainly more geology, more limestone passages, more geothermally influenced water, possibly biological material adapted to the extreme conditions, possibly geological signatures that would help us understand the cave's formation and its connection to deeper water systems. Significant, scientifically, potentially illuminating. But not a secret chamber with a treasure, not a portal to something unknowable, not a dramatic revelation, just more of what the cave already is, extending further down than we have yet been able to go. And that actually is enough. The significance of the Hranice Abyss does not depend on what is at the bottom. It depends on the fact that it is there at all, that a flooded cave in the Czech Republic is deeper than any other known flooded cave on Earth, that it is still geologically active, that it is still being dissolved deeper by processes that have been running for millions of years, and that we have not yet found where it ends. That is the story. It does not need embellishment. If you ever find yourself near Hranice, and it is a real place, accessible with a train station and a road and a small spa resort that still operates, you can stand at the edge of the lake and look at the water. It will be slightly warm. It will have that faint mineral smell. It will look green and calm and entirely ordinary. And you will know, if you have been paying attention, that the surface you are looking at is the top of something that descends further than most buildings at all, and then keeps going into the dark and the warmth and the slow chemical patience of the deep rock. That knowledge does not change what you see, but it changes what you understand about what you're seeing. That is, in a small way, what science does. It does not always make the world more dramatic, Sometimes it makes it more layered. It adds depth, literally in this case, to things that look simple from the outside. A lake becomes a shaft. A spa becomes a geological observatory. A quiet valley in Moravia becomes the location of the deepest known flooded cave on Earth, with no confirmed bottom, in a rock formation that has been there since before the first tree grew on land. There is something quietly wonderful about that. Not loud, not spectacular in the way that a film would frame it, just the steady, patient wonder of a world that keeps being more than it appears. So wherever you are tonight, whatever room, whatever city, whatever part of the world, there is rock beneath you. And beneath that rock, there are processes and structures and spaces that are still being mapped, still being measured, still being understood. Some of them have been there for hundreds of millions of years. Some of them we have not yet found. The Hranice Abyss is one of the ones we found but have not yet finished finding, and that is a good place to leave it for tonight. Not resolved, not closed, just acknowledged, sitting quietly in its valley in Moravia. The warm water rising from somewhere below, the surface still and green, the depth still open. Thank you for spending this time here, genuinely. This channel exists because there are people who want to sit with stories like this one. Careful, slow, patient stories about real places and real science and the parts of the world that do not get enough attention. If this was the kind of thing you come here for, then please do like the video and subscribe if you have not already. It helps more than you might think, and it means the channel can keep making things like this. And if you have a topic you would like to see covered, a place, a phenomenon, a question that has been sitting in the back of your mind, leave it in the comments. Some of the best episodes on this channel have come from suggestions left by people listening late at night, just like you might be doing right now. Where were you listening from tonight? What time was it? Was there water nearby, a river, a rain on the window, the distant sound of the sea? I'm always curious. Leave a comment if you feel like it. It is a small thing, but it makes the distance feel a little shorter. Sleep well if that is where you are headed. The cave will still be there in the morning, descending quietly into the dark, patient as limestone, deep as time,